Segment 1. The Basics and Identification. Welcome. Settle in wherever you are, whether you are lying down, resting your eyes, or simply letting the world slow to a quiet hum around you. You don't need to concentrate. You don't need to remember any of this. The only thing asked of you is to let these words wash over you gently and slowly, like a tide that never rushes, never demands, only arrives, and then recedes, and then arrives again. Tonight, we are going to travel somewhere remarkable, not in any hurried or dramatic way. We are going to drift slowly, out past the reach of everything familiar, out past the moon, past the great gas clouds where stars are born, past the edge of everything your eye could ever find in the darkest sky. And we're going to visit a world that, by all reasonable scientific understanding, should not exist. Its name is TOI-5205b. Say that quietly to yourself if you like. TOI-5205b. It is a strange, technical sort of name. The kind of name that sounds like a filing code or a serial number rather than the title of something vast and extraordinary. And, in a way, that is exactly what it is. It is a catalog entry, a designation, a way for scientists and astronomers scattered across the globe, working in observatories and universities and on supercomputers, to all know they are talking about the same impossible thing. But behind those letters and numbers, behind that quiet, unassuming name, is one of the most fascinating and genuinely puzzling objects that human beings have ever detected in the night sky. Let's begin at the very beginning. The name TOI-5205 becomes in 3 parts, and each part tells you something important, not just about this planet, but about how modern astronomy works, and how we find worlds that are so unimaginably far away that the light reaching us from their star left home before many of the greatest civilizations in human history had even begun. The first part of the name is the letters TOI. TOI. This stands for TESS Object of Interest. TESS is a space telescope, a remarkable piece of engineering that NASA launched in April of 2018, which has been quietly, patiently scanning the sky ever since. TESS stands for Transiting Exoplanet Survey Satellite, and its job, its singular, focused, methodical job, is to watch stars. Hundreds of thousands of stars. It watches them with a kind of patience that borders on the meditative, looking for the faintest, briefest dimming of starlight that might indicate a planet crossing in front of its host star, passing between us and that distant sun the way a moth crosses in front of a lamp on a warm summer evening. When Tess notices something, a dip in the light, a repeating pattern, a flicker that might be more than coincidence, it flags that star as an object of interest, a toy, something worth a closer look, something that says, "Here, pay attention, there may be something here." And so when astronomers around the world see the designation TOI-5205, they know immediately what that means. They know that the TESS satellite, drifting somewhere in its vast elliptical orbit around Earth, noticed something happening around the 5,205th object in its catalog worth investigating. They know that a tiny repeating shadow, so small it might seem like noise, like static, like nothing, was deemed significant enough to carry forward, to name, to study. That is the TOI. The number 5,205 is simply its order in the catalog. The 5,205th flagged object, a number that speaks to the sheer scale of modern astronomy, to how many stars Tess has watched, how many whispers of shadow it has noticed, how many possible worlds are waiting somewhere in the data to be confirmed and understood. And then comes the letter B. This small, quiet letter, just a single character, lowercase, tucked to the end of the designation, carries its own meaning. In the naming conventions that astronomers use for planetary systems, the star itself is given no letter at all, or is sometimes referred to as the anchor, the center, the thing everything else revolves around. And then the planets are named in the order they are confirmed. The first confirmed planet orbiting a star gets the letter B. The second would be C. The third, D. And so on. TOI-5205b carries the letter B because it is the first, and as of now, the only confirmed planet in the TOI-5205 system. It was the first shadow detected, the first gravitational whisper heard, the first world confirmed to be circling that particular star. And no other planets have yet been confirmed beside it. So it remains alone in its designation. A B with no C to follow, no D to come after. Just this one world in the catalog of a single quiet star. But if the name is technical and dry, the nature of this planet is anything but. Somewhere along the way, sometime after its discovery was confirmed and published, sometime after scientists began to understand just how extraordinary and how baffling its very existence is, TOI-5205b was given an informal name, a nickname, the kind of name that scientists tend to reach for when data alone cannot fully capture how unusual something is. They call it the Forbidden Planet, not because it is off-limits, not because some governing body of astronomy has restricted access to it. The nickname carries no legal weight, no regulatory meaning. It is forbidden in a deeper, more conceptual sense, in the sense that this planet represents a combination of circumstances that are best scientific models, our most carefully constructed theories about how planets form and how solar systems take shape. Said simply, could not happen that IT should not be here. The math said it could not be here. The models said that the conditions necessary to grow a planet like this one around a star like this one did not exist. And yet here it is, the Forbidden Planet. There's something deeply compelling about that phrase when you hold it against the vastness of space. We human beings build our understanding of the universe piece by piece, observation by observation, theory by theory. We construct elegant frameworks for how gravity behaves, how gas and dust collapse into stars, how the leftover material swirls and clumps and slowly becomes planets. We have learned so much. We have mapped galaxies and measured the expansion of space and detected the echoes of the very first light that existed after the Big Bang. And still, the universe surprises us. Still, it presents us with things that sit outside the frame of our understanding, that don't fit the picture we have so carefully assembled, that force us to go back to the equations and ask whether we got something wrong, or whether we simply hadn't considered something yet. TOI-5205b is one of those surprises. It is classified in the language of planetary science as a gas giant. This is a meaningful category. Gas giants are the enormous, billowing worlds made primarily of hydrogen and helium, the lightest and most abundant elements in the universe, rather than rock and metal and solid ground the way Earth is. In our own solar system, we have two gas giants that most people know well, Jupiter and Saturn. Jupiter is immense. It is so large that more than 1,300 Earths could fit inside it. Its atmosphere is a swirling cauldron of storms and winds, and the famous Great Red Spot, a storm system so large it could swallow our entire planet, has been raging for centuries, possibly longer. Saturn is hardly smaller, and it carries those extraordinary rings of ice and dust that make it one of the most visually striking objects in the solar system. Both worlds are gas giants, dominated by atmosphere layered in clouds, with no solid surface to stand on, only deepening pressure and heat as you descend toward whatever lies at their cores. TOI-5205b belongs to this family. It is a gas giant in the tradition of Jupiter and Saturn, a world of atmosphere and depth, a world without a surface, a world made of the simplest and most ancient materials in the universe. This alone makes it a fascinating object. Gas giants are dramatic, extreme, awe-inspiring in their scale. But where this one exists, and the circumstances under which it came to exist, is where the story becomes truly astonishing. To understand why, we need to think about where TOI-5205b lives, not its position in space in some abstract sense, but the specific address, the neighborhood, the local architecture of light and gravity that defines its daily existence. TOI-5205b orbits a star. Its star, the sun of its solar system, the center of its gravitational world, is called TOI-5205. And TOI-5205 is a red dwarf. Red dwarfs are, by far, the most common type of star in the known universe. If you were to count every star in our galaxy, all the hundreds of billions of them scattered across the Milky Way, somewhere around 70 to 75% of them would be red dwarfs. They are everywhere, and yet they are so faint, so small, so dim, that not a single one of them is visible to the naked eye from Earth. The closest star to our own sun, Proxima Centauri, is a red dwarf, and even at a mere 4 light-years away, cannot be seen without a telescope. Red dwarfs are small. They burn cool compared to stars like our sun. Their light is dim and reddish, shifted toward the infrared end of the spectrum. They are steady and quiet and extraordinarily long-lived. A red dwarf can burn for trillions of years before exhausting its fuel, outlasting our own sun many times over. And they are, by the models and theories that scientists have built, not supposed to be very good at producing gas giants. The reasoning goes like this. To form a gas giant, you need a significant amount of rocky material to gather together first. A solid core, massive enough to gravitationally attract and hold on to enormous quantities of gas. That initial gathering of solid material requires a disk of planetary forming matter around the young star to be rich enough, dense enough, generous enough with its resources to allow a core that large to assemble before the star's own energy disperses the gas disk away. Red dwarfs, being small and cool, tend to have smaller, less material-rich disks. The math suggested that around stars as small as TOI-5205, a Jupiter-sized world simply couldn't grow fast enough from a disk modest enough to achieve what TOI-5205b appears to have achieved. And yet, here it is. Now, the system itself occupies a corner of the sky that has its own gentle poetry. TOI-5205 is located in the constellation Vulpecula. The name comes from Latin. It means the little fox. It is a small, faint constellation in the northern sky, tucked between more prominent star patterns in the region of the summer Milky Way, not far from the bright star Altair, and the easily recognized shape of the arrow-shaped constellation Sagitta. Vulpecula contains no particularly bright stars of its own, and many people who consider themselves familiar with the night sky may have never consciously identified it. It is one of those quiet constellations, easy to overlook, requiring patience and dark skies to trace. And somewhere in that modest patch of sky, embedded in a region of space too far for the eye alone to reach, is the star TOI-5205, and in orbit around it, the world we have come to call the Forbidden Planet. How far away is it? The distance, when given as a raw number, is one of those quantities that sound significant, but is difficult to truly feel. TOI-5205b is approximately 283 light-years from Earth. A light-year is the distance that light, the fastest thing in the physical universe, traveling at roughly 186,000 miles per second, covers in the span of 1 full year. In 1 second, light can travel from New York to Los Angeles more than 60 times. In 1 year, light covers an almost incomprehensible distance. And the Forbidden Planet is 283. What that means in practical terms is this. The light that left the TOI-5205 system and is arriving at our telescopes right now, the light that allowed us to detect, to study, to confirm this world, left its origin point approximately 283 years ago. It left in the 1740s, roughly speaking. It left when Bach was still composing, when the American colonies were still decades away from revolution, when the steam engine had not yet transformed human civilization. That light has been traveling through the void ever since, crossing the dark between stars, carrying its quiet information forward through centuries of human history, and arriving, finally, at the sensors of a space telescope orbiting the Earth. And in that ancient light, we found a planet that should not exist. It is entirely inhospitable to life as we know it. This much can be said with comfortable certainty. A gas giant, by its very nature, offers no solid surface on which life could gain a foothold, no stable ground, no liquid water in any of the forms that biology, as we understand it, tends to require. The pressures deep within TOI-5205b would be crushing. Its proximity to its star, which we will explore more fully as we continue, means the temperatures it experiences are extreme. It is not a place that life, in any form recognizable to us, could navigate or survive. This does not make it less interesting. If anything, it makes it more so. The universe does not need to be habitable to be extraordinary. The forbidden planet is not extraordinary because it might harbor life. It is extraordinary because it exists at all. And perhaps nothing captures just how extraordinary it is, quite like this final observation about TOI-5205b. It represents one of the most extreme mass ratios between a star and an orbiting planet that astronomers have ever measured. The star TOI-5205 is small for a star, small compared to our own sun. And the planet orbiting it, TOI-5205b, is enormous relative to it. Enormous in a way that strains the models, that challenges the equations, that forces scientists to ask whether something is missing from their understanding of how worlds are born. Think of it this way. Imagine holding a basketball. Now imagine balanced on the edge of that basketball, caught in orbit, is a marble, not a tiny marble, but a respectable, substantial marble. That rough visual proportion is closer to what you have in most planetary systems involving gas giants, a large star, and a comparatively modest planet. But the ratio in the TOI-5205 system is more extreme than that. The planet, relative to its star, is unexpectedly, almost implausibly, large. It is as if the marble had grown, as if something had allowed it to accumulate far more than the models said was available. Scientists who study planetary formation have specific terms for this. They talk about mass ratios, about protoplanetary disk masses, about core accretion timescales. But underneath all the technical language is a simpler statement. By our best current understanding of how solar systems form and evolve, what we see around TOI-5205 should not be there. The forbidden planet earned its name honestly. And so, as you rest here, as your breathing slows and the weight of the day lifts a little further away with each passing moment, hold that image gently in your mind, if you like. A small, dim, ancient star, burning quietly in a patch of sky called the Little Fox. A planet circling it that is too large, too massive, too improbable. A world that broke the rules just by existing. A discovery that arrived at our instruments on light that left its source in the time of powdered wigs and harpsichords, and told us, quietly, insistently, without drama, that our picture of the universe is still incomplete. You don't need to solve that puzzle tonight. Nobody does. The universe has kept its secrets for 13 billion years, and it is in no hurry to surrender them. Neither are you in any hurry. There is nowhere to go, nothing to figure out. Only this, only the slow, gentle turning of the world beneath you, and the thought of a planet impossibly far away, impossibly improbable, existing in quiet defiance of everything we thought we knew. Let that be enough for now. Let that carry you forward into the soft, dark quiet that is waiting for you just ahead. Rest. Segment 2. The Forbidden Anomaly. There's something quietly humbling about the idea that the universe does not consult our textbooks before deciding what to do. We are a species that loves to understand things. We are, perhaps more than anything else, pattern seekers. Creatures who look at the chaos of experience and reach instinctively for the underlying rule, the organizing principle, the equation that makes sense of what we see. It is one of our most remarkable qualities. It is the impulse that gave us mathematics and physics and chemistry, that allowed us to predict the motion of planets centuries before we could visit them, that let us calculate the existence of black holes decades before we had instruments sensitive enough to detect one. And it is the same impulse that, over many decades of careful observation and rigorous thought, gave us a theory for how planets form, a framework, a model, a set of rules that seemed, based on everything we had seen, everything we had measured, everything our most powerful computers could simulate, to describe how gas, dust, and gravity conspire to build worlds. That framework is called the Standard Model of Planetary Formation, and TOI-5205b. The Forbidden Planet breaks it, not bends it, not strains it slightly around the edges, breaks it in the clean and unambiguous way that a single unexpected observation can sometimes break a model that had seemed perfectly adequate until that moment. To understand what makes this planet so disruptive, it helps to understand the model it disrupts, and the central idea within that model, the mechanism that scientists have long believed is responsible for producing gas giants like Jupiter and Saturn, is a process called core accretion. Core accretion is, at its heart, a beautifully logical idea. It begins in the early life of a solar system, when a young star has just formed from a collapsing cloud of gas and dust, and all around it, orbiting like a vast, flat, slowly rotating disk, is the leftover material from that collapse. Dust and pebbles and icy chunks and gas, all swirling in a wide, thin disk around the newborn star, gradually settling and interacting and colliding with one another. In the core accretion model, the first step is the slow accumulation of solid material. Tiny grains of dust stick together. Pebbles gather into boulders. Boulders over long time scales accumulate into larger bodies. Bodies that are massive enough to begin attracting more material through gravity, growing steadily, pulling in more and more solid rock and ice from the surrounding disk. Over millions of years, this process can produce a planetary core, a dense, solid, rocky object, perhaps several times the mass of Earth, sitting embedded in the disk like a seed. And that seed, that accumulated rocky core, is what triggers the next step. Because once a core becomes massive enough, something remarkable happens. Its gravitational pull becomes strong enough not just to gather more rocks, but to attract and hold on to the surrounding gas. The lightweight hydrogen and helium that fill the disk begin to fall inward toward the core. Slowly at first, then faster, as the growing envelope of gas adds its own gravitational weight to the pull. The core reaches a critical threshold, a tipping point, and beyond that point, gas accumulates rapidly. In a relatively short time, by planetary formation standards, a gas giant is born. This is the core accretion model. And for most of the solar systems we have observed, it explains what we see quite well. It explains why gas giants tend to form at certain distances from their stars, far enough out that icy materials are available to help build the core, in regions where the disk is rich enough in solid material to allow a substantial core to grow. It explains the rough proportions of planets we tend to find: rocky planets close to stars, gas giants farther out. It explains a great deal, but it comes with requirements, conditions that must be met. And the most fundamental of those conditions is this: there must be enough solid material in the protoplanetary disk to build the core in the first place. This is where TOI-5205b becomes a problem, because the star that TOI-5205b orbits, the quiet, dim, small red dwarf designated TOI-5205, is not a large star. It is, in stellar terms, quite modest. And stars like this one, when they are young and surrounded by their protoplanetary disks, do not tend to have very generous disks. The disk of a red dwarf is typically smaller, less massive, less richly endowed with the solid materials needed to build planetary cores than the disk of a larger, brighter star like our own sun. Think of it as a kind of cosmic budget, a finite amount of raw material available for the star to spend on building planets. Our own sun had a substantial budget. It built 8 planets, countless moons, and still had enough left over to fill the asteroid belt and Kuiper belt with billions of smaller objects. A red dwarf like TOI-5205 has a much smaller budget, less dust, less rock, less of everything that core accretion needs. And the calculation. When you sit down and do the math, when you plug in the mass of the star and estimate the likely mass of its protoplanetary disk, and ask how much solid material was available to be gathered into a core, comes up short by a significant margin. The number suggests that the disk around TOI-5205 simply should not have contained enough rocky material to build a core massive enough to trigger the runaway gas accretion that produces a Jupiter-sized planet. The disk mass deficit is not a subtle discrepancy. It is not a small fudge factor, not a rounding error, not an anomaly that can be quietly absorbed into the uncertainty bars of a graph. It is a genuine, substantive gap between what the model predicts should be possible and what we actually observe. TOI-5205 had, according to our best estimates, a disk too lean and too modest to have built what it built. And yet it built it. Somewhere in that disk, from those inadequate raw materials, the universe assembled a planet larger than Jupiter. It did so around a star so small that the planet's mass relative to the star's mass creates a ratio that ranks among the most extreme ever discovered. It did so in defiance of the Standard Model's predictions. And this defiance sends scientists back to the drawing board, not in despair, but in that particular flavor of intellectual excitement that comes when the universe reveals that it knows something you don't. One of the first questions that the discovery of TOI-5205b forces onto the table is a question about time, not just about materials, but about the speed at which those materials could have been assembled into something planet-sized. Because core accretion, as traditionally understood, is a slow process. It takes time, sometimes tens of millions of years, for dust to stick to pebbles, for pebbles to become boulders, for boulders to accumulate into a core of sufficient mass. And there is a deadline, a hard deadline imposed by the physics of the disk itself. The gas in a protoplanetary disk does not last forever. The young star, once it ignites fully, begins to blow that gas away, a process driven by stellar radiation and a stream of charged particles called the stellar wind. Within a few million years, typically, the gas disk is gone. And once the gas is gone, the window for forming a gas giant closes forever. No gas in the disk means no gas giant. The opportunity has passed. If core accretion is as slow as our models suggest, and if the disk disperses within a few million years, then around a star with a disk as modest as TOI-5205's, a gas giant simply cannot make in time. The core would still be growing when the gas blows away. The game would be over before the winning move could be played. But TOI-5205b exists, which means either the game played out faster than we thought possible, or the rules of the game are different from what we assumed. The existence of this planet implies, strongly, that planetary formation can happen much faster and much earlier in a star's life than our current models predict. That somewhere in the early chaos of a forming solar system, there is a pathway, an accelerated route, through which solid material can accumulate into a core on timescales short enough to beat the gas dispersal deadline, even in a disk that doesn't seem to have much to work with. And this possibility has directed scientific attention toward an alternative mechanism, a different way of building planetary cores that is faster, more efficient, and potentially operative even in modest-sized disks. It is called pebble accretion. The idea behind pebble accretion is elegant and, to many scientists, deeply compelling. In the traditional core accretion picture, the building blocks of a planetary core are relatively large: boulders, kilometer-sized objects, clumps of rock and ice that collide and merge slowly over long timescales. Pebble accretion proposes something different. It suggests that the most important building blocks are much smaller, centimeter-scale pebbles, drifting through the protoplanetary disk, carried inward by the subtle aerodynamic drag of the disk's gas. These pebbles, because of their size and the way they interact with the gas around them, are swept up by a growing planetary embryo with remarkable efficiency. A body that has already accumulated a modest amount of mass, a planetesimal, perhaps the size of a large asteroid, can capture drifting pebbles at a rate far exceeding what traditional boulder-to-boulder collision models predict. The pebbles spiral inward, pulled by gas drag and gravity, and fall onto the growing core in a continuous rain rather than in the occasional violent collision of large bodies. The result, in theory, is a dramatic acceleration in the growth of planetary cores. What might take tens of millions of years in the traditional model might happen in a fraction of that time through pebble accretion. The core grows faster. It reaches the critical threshold for gas accumulation earlier. It beats the clock imposed by disk dispersal. TOI-5205b has not proven that pebble accretion is the correct explanation for its existence. Science rarely works in such clean and direct confirmations. But its existence has given pebble accretion a renewed urgency in scientific discussions. It has pushed researchers to look more seriously at this mechanism, to refine their models of it, to ask whether it can operate efficiently enough around a star as small as TOI-5205 to produce what we see today. Because before TOI-5205b was found, the consensus, the quiet working assumption of much of the planetary science community, was that gas giants were, at most, exceedingly rare around M-dwarf stars. An M-dwarf is the technical designation for a red dwarf, a low-mass star, cool and dim, the most numerous type of star in the galaxy. The assumption was that M-dwarfs simply could not produce gas giants in meaningful numbers. Their disks were too small, their material budgets too limited, the timescales too challenging. Gas giants were for larger, more generous stars. The discovery of TOI-5205b challenges that assumption directly. It does not necessarily mean that M-dwarfs commonly produce gas giants. One example does not a trend make, but it proves unambiguously in the irreversible way that real observations always trump theoretical assumptions, that an M-dwarf can produce a gas giant, that the process, whatever it is not impossible around these stars, that the door we thought was closed is at least ajar. And there is a further consequence of this planet's existence, one that follows from the very thing that makes it so improbable. If building TOI-5205b required almost all of the rocky material available in the protoplanetary disk around TOI-5205, then that material, by definition, is no longer available. It was spent, consumed, gathered into the core of this one enormous planet, which means that the TOI-5205 system is unlikely to harbor large planetary siblings. No second gas giant waiting farther out in the same system. No competing Jupiter on the other side of the disk. The resources for building such a sibling were already gone, used up in the construction of this one improbable world. TOI-5205b, if this reasoning is correct, built itself at the expense of everything else that might have existed in the same system. It is, in this sense, an only child, and a remarkably demanding one at that. This picture of the forbidden planet, isolated, enormous, improbable, the sole large product of a disk that probably should not have been able to produce it, is one of the things that makes this system so philosophically interesting to sit with. The universe allocated a modest amount of raw material to this little corner of the galaxy. And in that modest allocation, instead of building several small worlds and distributing the resources across them, it concentrated everything into one object. One gas giant, one exception. It is, in a sense, a profligate choice, a lavish, extravagant expenditure of everything available on a single result that the standard model said couldn't happen. And what that tells us, what TOI-5205b proves, quietly and simply just by being there, is that the universe is capable of building enormous planets from a surprisingly sparse amount of starting material. That the efficiency of planet formation, at least under some circumstances and by some mechanisms not yet fully understood, exceeds what our best computer simulations can currently replicate. That our models of how solar systems assemble themselves are incomplete. This is not a failure of science. It is science working exactly as it should, observation pressing against theory, reality refusing to be fully contained by our equations, the universe insisting on its own complexity. The computer simulations that cannot currently reproduce TOI-5205b are not wrong. Exactly, they are incomplete. They are the best approximation we have built so far. And now, with this impossible planet as a data point, scientists can begin to ask what ingredient is missing from the simulation. What physical process is underweight or unrepresented, or absent entirely from the model? Pebble accretion is one candidate. There may be others. There may be combinations of mechanisms, chains of events in the early life of a solar system that conspire to produce, occasionally, a world that stands outside the predicted range. The discovery of TOI-5205b does not hand us the answer, but it sharpens the question considerably. And so the forbidden planet earns its name not once, but repeatedly, at each new level of examination. It is forbidden by the mass of its host star's disk. It is forbidden by the timescales of core accretion. It is forbidden by the previous consensus that M-dwarfs don't do this. It is forbidden, in a sense, by the entirety of our theoretical framework for how solar systems come to be. And yet there it is, orbiting its small, dim star, persisting in the sky, carrying its letter B like a quiet badge of distinction, the first, and so far only, confirmed planet in a system that had no business producing it. There's something almost peaceful in that image, if you let it settle into you rather than trying to resolve it. The universe building something that, according to everything we understand, it could not build. The rules being broken not by any dramatic disruption, not by any exotic physics or strange exception, but simply by the slow, patient, ordinary process of gravity and gas and time, working just efficiently enough, just fast enough, in ways we have not yet fully mapped. The universe did not ask permission. It did not consult the model. It gathered what was available, and it built something extraordinary with it. Let that thought carry you. Let it settle into whatever quiet space is opening up inside you as the world grows still. The forbidden planet is out there, 283 light years away, circling its little fox-shaped corner of the sky. Proof that nature is always working with more resources than we have given it credit for. More cleverness, more efficiency, more capacity for the improbable than our most careful mathematics has yet managed to express. You don't need to understand it fully. You don't need to hold all the details. Just let the shape of it rest in your mind, gently, loosely, the way a stone rests at the bottom of a slow, clear river. Something impossible, calmly existing. Segment 3, the host star, TOI-5205. Before we can truly know a planet, we must first know its star. This is true in the most literal, practical sense. Astronomers studying a distant world must measure and characterize its host star carefully before they can say anything reliable about the planet orbiting it. The star's size, its mass, its temperature, its brightness. All of these quantities flow directly into the calculations that tell us how large the planet is, how massive, how close, how hot. The star is the anchor, the reference point, the known quantity against which the planet is measured. But it is also true in a deeper, more poetic sense. A planet is, in almost every meaningful way, a child of its star. It formed from the same cloud of material that gave birth to the star. It has spent its entire existence bathed in the light and radiation that the star produces. Its temperature, its atmosphere, its chemistry, its history, all of it has been shaped continuously and profoundly by the star at the center of its world. To understand a planet is, in large part, to understand the star it calls home. And so tonight, we turn our attention to TOI-5205 itself, the host star, the small, ancient, quietly burning heart of this system. The first thing to know about TOI-5205 is its classification. In the system that astronomers use to categorize stars, a system built on temperature and color and the patterns of light that each type of star produces, TOI-5205 is designated as an M4 type main sequence star. That description contains a great deal of information, compressed into a small number of characters, in the efficient way that scientific nomenclature tends to work. The M in M4 refers to the spectral class. Stars are sorted into spectral classes based on their surface temperature, from the hottest and bluest at the top of the sequence, through yellows and oranges, and into the cool, dim, reddish stars at the lower end. Our own Sun is a G-type star, a middle-of-the-road, moderately warm, yellow-white star. An M-type star sits at the coolest end of the main sequence. It is the dimmest, the smallest, the least luminous of the main categories. The 4 that follows the M is a refinement within that category. M-type stars range from M0, which are the warmest and largest of the red dwarfs, down to M9 and beyond, which are extraordinarily faint and small, barely larger than some gas giant planets. An M4 sits in the middle of this range, a fairly typical red dwarf in many respects, though as we will see, it carries at least one characteristic that makes it stand out from the crowd. The designation main sequence is equally important. The main sequence is not a place, it is a state of being. A star is on the main sequence when it is in the stable, sustained phase of its life, during which it fuses hydrogen into helium in its core, releasing the energy that makes it shine. Our Sun is on the main sequence. TOI-5205 is on the main sequence. A star remains on the main sequence for the bulk of its existence, and only leaves it when the hydrogen fuel in its core begins to run out, triggering the changes that eventually lead to the end of the star's life as we know it. TOI-5205 is a main sequence star, which is to say it is in its long, stable, productive middle life. That middle life, as we shall see, is likely to be almost incomprehensibly long. But before we get there, let us sit for a moment with the simplest and most striking facts about this star, the numbers that tell us what it is in the most immediate physical terms. TOI-5205 is small, remarkably small, by the standards of the stars most people are familiar with. Its mass, the total amount of material it contains, is only about 39% of the mass of our Sun. Less than half. If you could somehow place our Sun on one side of a cosmic scale and TOI-5205 on the other, you would need more than 2.5 of TOI-5205 to balance the weight of our own star. It is, by the measure of mass, a modest object, though of course, in absolute terms, it is still an almost incomprehensibly large concentration of matter, containing hundreds of thousands of times the mass of the Earth. Its radius, the distance from its center to its surface, tells a similar story. TOI-5205 is roughly 39% the radius of our Sun as well. This near equality between the star's mass fraction and its radius fraction is characteristic of red dwarfs in this part of the M-dwarf sequence. They are dense, compact objects, smaller and more tightly packed than the larger stars higher up the spectral sequence. And the size of this star, its physical radius, the actual span of it from one side to the other, brings us to one of the most striking individual facts about the TOI-5205 system, one that is worth pausing on and letting settle fully into your imagination before moving past it. TOI-5205 is only slightly larger than the planet Jupiter. Take a moment with that. Our own Sun is enormous compared to Jupiter. You could fit more than 1,000 Jupiters inside the Sun by volume, and the Sun's diameter is roughly 10 times that of Jupiter. The Sun and Jupiter, placed side by side, have a size relationship that makes the disproportion immediately clear to any eye. The Sun is a vast, blazing sphere. Jupiter, against it, is a marble. But TOI-5205 is not our Sun. TOI-5205 is such a small star that its physical size barely exceeds that of a gas giant planet. The planet orbiting it, TOI-5205b, is itself a gas giant, likely in a similar size range to Jupiter, which means that in the TOI-5205 system, the star and its planet are not in a relationship of overwhelming disproportion, the way a star and planet typically are, but are instead something more unusual. Two large, roughly comparable objects, one slightly bigger than the other, locked together in their gravitational dance. This is one of those facts that becomes more astonishing the longer you sit with it. A star, a thermonuclear furnace, a self-sustaining fusion reactor, something that generates its own light and heat through the compression of matter at its core, that is only marginally larger than one of its own planets. It is a reminder of just how varied the universe is in its constructions, how wide the range of possible sizes and configurations of matter can be, how the categories we use, star, planet, gas giant, red dwarf, are human labels imposed on a continuous spectrum of physical possibilities. Of course, despite its modest size, TOI-5205 is unmistakably a star. The difference between even the smallest stars and the largest planets is not just one of size, but of internal physics, of what is happening in the core. Stars fuse hydrogen. Planets, including gas giants, do not. TOI-5205, despite being barely larger than Jupiter in physical dimensions, is undergoing nuclear fusion at its center, converting hydrogen to helium and releasing the energy that gives it whatever dim glow it has. Jupiter is not. This distinction is fundamental and real, even if the size difference between the two types of objects, in this particular case, is far less dramatic than most people would expect. Now, the temperature of TOI-5205 surface. Numbers, when they describe something as alien as stellar physics, can be hard to feel, but this one is worth dwelling on. The surface of TOI-5205 burns at approximately 3,430 Kelvin. For context, our own Sun's surface sits at around 5,778 Kelvin. The difference between those two numbers, roughly 2,300 degrees, is not a small gap. It represents an enormous difference in the character of the light each star produces. Heat and light are intimately connected. The hotter a surface is, the more energetically it radiates, and the shorter the wavelengths of the light it preferentially emits. Our Sun, at nearly 5,800 Kelvin, radiates most strongly in the visible part of the spectrum. the light our eyes evolved to see, the warm yellow-white that floods our days and gives color to everything we perceive. TOI-5205, at 3,430 Kelvin, radiates much more weakly, and it radiates most strongly not in visible light, but in the infrared. Wavelengths longer than what human eyes can detect. Warmth rather than light, in a sense, energy that we would feel as heat rather than see as brightness. This means that if you could somehow stand near the TOI-5205 system and look toward its star with naked human eyes, the star would appear dim and deeply reddish, far redder than our sun, far dimmer than even the reddest sunset you have ever witnessed. It would not flood the sky with the kind of brilliant white-yellow radiance we associate with daytime. It would be a subdued ember in the sky, present warm, but not blazing. The sky of any world in this system would likely look profoundly different from ours. Darker, more muted, the illumination richer in wavelengths we cannot quite see. And because it is so cool and so small, TOI-5205 is extraordinarily dim. Its luminosity, the total amount of energy it pours into space every second, is a tiny fraction of our sun's output. The sun is a generous radiator of energy. TOI-5205 is parsimonious, conservative, careful with its fuel. It emits a trickle of energy compared to what our own star broadcasts outward in every direction. Most of what it does emit is in the infrared, invisible to the human eye, carrying energy that warms without illuminating in any way we could directly perceive. This characteristic, the emphasis on infrared radiation, the relative scarcity of visible light, has significant implications for any world orbiting this star. The planet TOI-5205b, which we will continue to explore in later segments, is heated primarily by infrared radiation from its host. The energy budget of that planet, the way radiation interacts with its atmosphere, the photochemistry that might occur in its upper cloud layers, all of it is shaped by the unusual spectral quality of the light its star provides. Infrared-dominated starlight is not the same as the visible-dominated sunlight that drives the atmospheric chemistry and dynamics of the planets in our own solar system. It is a different kind of illumination entirely, with different consequences. One of the most remarkable facts about TOI-5205 and about red dwarfs in general is the sheer abundance of these stars in the Milky Way. We mentioned this in passing in an earlier segment, but it deserves a fuller moment of appreciation. Red dwarfs are not curiosities. They are not exotic exceptions. They are the dominant form of stellar life in our galaxy. Of all the hundreds of billions of stars in the Milky Way, all the yellows and whites and blues and oranges scattered across the spiral arms, somewhere around 70 to 75% of them are red dwarfs, M-type stars. Cool, small, dim. The night sky as we see it is populated almost entirely by stars that are not like this, by larger, brighter objects that are visible precisely because their luminosity is exceptional. The most common type of star in the galaxy is almost entirely absent from the naked eye view of the sky, because individual red dwarfs are simply too faint to see. Proxima Centauri, the closest star to our own sun, is an M dwarf, and even at just over 4 light-years away, it is invisible without a telescope. The sky of our night is a biased sample, showing us the brightest things rather than the most common ones. TOI-5205 is one of the vast, invisible majority, one of the uncountable red dwarfs that populate the galaxy, and that, until relatively recently, were thought to be unlikely hosts of complex or interesting planetary systems. The discovery of TOI-5205b, a gas giant around one of these common modest stars, asks us to reconsider how we think about all of those billions of dim, unremarkable-looking stars, and what might be orbiting them in the dark. Now, the metallicity. This is a term that astronomers use in a somewhat specialized way, one that can be initially surprising if you encounter it without context. When astronomers say that a star is metal-rich, They do not mean what the word metal typically implies in everyday usage. In stellar physics, a metal is any element heavier than helium. Hydrogen and helium are the two original elements, the ones that filled the universe in its earliest moments after the Big Bang. Everything else, carbon, oxygen, silicon, iron, gold, all of the heavier elements that make up rocks and atmospheres and living things, is, in the astronomer's vocabulary, a metal. These heavier elements were forged in the interiors of previous generations of stars and scattered into space when those stars died. A star that is metal-rich contains a relatively high proportion of these heavier elements compared to a star of similar type. And TOI-5205, it turns out, is slightly metal-rich. It contains a somewhat higher abundance of elements heavier than helium than our own sun does, or than a typical star of its type. This is significant, and not merely as a curiosity. Metallicity is known to correlate with planet formation. Stars that are more metal-rich tend to more commonly host planets, and especially larger planets, because the heavier elements in the protoplanetary disk provide the solid, rocky building blocks from which planetary cores assemble. A metal-rich disk has more of the raw material needed to build planets. It is richer in the ingredients that matter. The fact that TOI-5205 is slightly metal-rich may therefore be part of the story of how its impossible gas giant came to exist. Even if the disk was overall smaller and less massive than those around larger stars, the slightly elevated concentration of heavy elements might have provided a modest but meaningful advantage. A slightly denser supply of solid material, a slightly richer base from which a planetary core could begin to grow. It does not fully resolve the puzzle. The numbers still do not add up neatly even with this boost, but it may be one piece of an answer that, in total, is still being assembled. And then there is the question of lifespan, which is perhaps the most humbling fact of all about stars like TOI-5205. Our own sun is approximately 4.5 billion years old. It has been burning for 4.5 billion years, and it has enough hydrogen fuel remaining at its core to continue fusing for roughly another 5 billion years. 10 billion years total is our sun's working life. This already exceeds human comprehension almost entirely. The 4.5 billion years our sun has already lived contains all of Earth's history: the formation of the planet, the first life, the great extinctions, the rise of complex organisms, the entirety of human civilization, everything, squeezed into just the first half of an already staggering span. But red dwarfs burn their fuel so slowly, so carefully, so conservatively, because their lower mass means lower core pressure means slower fusion reactions, that they can remain on the main sequence for timescales that dwarf even our sun's generous lifespan. TOI-5205 will likely shine for hundreds of billions of years. Some estimates for stars in this class suggest lifespans approaching 1 trillion years, a number so far beyond the current age of the universe that it becomes almost philosophical. The universe itself is only about 13.8 billion years old. TOI-5205 may shine for 70 or 80 times longer than the universe has currently existed. This means something quietly extraordinary. TOI-5205 is almost certainly a young star in the context of its own life, whatever age it is now, and red dwarfs can be billions of years old already. It has almost incomprehensible amounts of future ahead of it, if planetary systems around M-dwarfs are common, and if some of those planets have the conditions for interesting chemistry or even life. Those systems have an almost unimaginable amount of time to develop and evolve. Billions upon billions of years of stable starlight, slowly and steadily warming whatever orbits nearby. For TOI-5205b, this longevity means something specific. It means the gas giant has been orbiting its small star for a long time already. and will continue to do so for far longer into the future than our entire solar system has even existed. The planet's relationship with its star is not a brief arrangement. It is one of the most enduring configurations in the galaxy. But that long, stable relationship is not entirely peaceful. Because red dwarfs, for all their quiet, conservative, slow-burning ways, are not always calm. They carry a secret violence in their magnetic fields. Stars generate magnetism through the churning of electrically charged plasma in their interiors. The same physical process that gives our own sun its 11-year activity cycle, its sunspots, its periodic solar flares. In red dwarfs, this magnetic activity is often proportionally much more extreme relative to the star size than it is in larger stars like our own. M-dwarfs like TOI-5205 are known to produce powerful stellar flares, sudden, violent releases of energy from the star surface as magnetic field lines that have become tangled and stressed snap back and reconnect. These flares can release, in a matter of minutes, enormous amounts of energy across the entire electromagnetic spectrum, including ultraviolet radiation and X-rays. They are, relative to the star's normal output, far more dramatic than the solar flares our sun produces. An M-dwarf flare can briefly increase the star's total energy output by a significant fraction. Some of the most powerful M-dwarf flares ever observed have temporarily brightened their stars by tens of %. For TOI-5205b, bathed in the light and radiation of its host star and orbiting at a relatively close distance, these flares represent a regular bombardment of high-energy radiation. The planet receives pulses of ultraviolet and X-ray energy with a frequency and intensity that would be entirely alien to our experience of living around a relatively well-behaved, middle-aged, moderate star like our sun. For a gas giant, this radiation interacts primarily with the upper atmosphere, potentially stripping away lighter gases, driving photochemical reactions in the cloud layers, shaping the long-term evolution of the atmosphere in ways that models are only beginning to explore. It is one more element of the extreme and complicated environment that TOI-5205b inhabits. And so the host star, when you see it whole, is a study in contrasts. It is small and dim and cool and conservative and ancient in the making and extraordinarily long-lived. It burns gently. It emits mostly warmth rather than brilliance. It is the most common type of star in the galaxy, and yet invisible to the naked eye. It is slightly richer in the heavy elements that matter for planet formation, and it occasionally erupts with magnetic violence that belies its otherwise quiet character, sending pulses of energy washing over the improbable planet in its orbit. This is the star that should not have made a gas giant. This is the star that did anyway. It is not a dramatic star in the way that the brightest stars in our sky are dramatic, not blazing blue-white giants, not pulsing variable stars, not stars on the edge of supernova. It is modest and quiet and in most observable respects, utterly ordinary for its type. And yet the planet it harbors has made it one of the most discussed stellar objects in the recent literature of exoplanet science. There is something in that worth appreciating as you drift toward sleep. The universe does not always put the most extraordinary things inside the most spectacular containers. Sometimes the improbable and the wondrous live inside the smallest, quietest, most unassuming of vessels. A dim red ember in the sky, barely larger than the planet it hosts, burning so slowly it will outlive the current age of the universe many times over. and around it, a gas giant that no one expected, orbiting in patient, impossible silence. Let the image settle. The small, warm star, the giant planet in its orbit, both of them dim and distant, 283 light-years away in the constellation of the Little Fox, doing together what the models said could not be done. You don't need to understand it. You only need to let it be there, somewhere at the edges of your awareness, as everything quiets. Segment 4, Orbital Dynamics. There is a particular kind of stillness that comes in the very late hours of the night, when the world has gone quiet and the only thing moving is your own slow breath. Everything has slowed down. The urgency of the day has dissolved. Time itself seems to soften, to lose its sharp edges, to become something more like a gentle current than a rigid structure. Hold that feeling for a moment. The feeling of time moving differently than it does in the busy hours. Because the planet we are visiting tonight experiences time in a way that is so extreme, so compressed compared to our own experience of days and years and seasons, that it asks us to genuinely loosen our grip on what those words mean. We have already learned that TOI-5205b is a gas giant, enormous, improbable, orbiting a small red dwarf star in a corner of the sky called the Little Fox. We have learned that it should not exist according to our best models, and that it does anyway. We have learned about its star, dim, cool, ancient in its potential, quietly violent in its magnetism. Now we turn to the orbit itself, the path that TOI-5205b traces around its star, the shape and speed and consequences of that journey. And what we find when we look closely at the orbital mechanics of this planet is a world living at an extreme that makes even the most dramatic conditions in our own solar system seem mild by comparison. Let us begin with the most immediately striking fact: the length of a year on TOI-5205b. A year, in the most fundamental sense, is the time it takes a planet to complete one full orbit around its star. For Earth, that duration is approximately 365¼ days, a number so woven into the fabric of human culture and biology and agriculture and history that it feels almost like a natural constant rather than an accident of orbital mechanics. For Mars, a year lasts about 687 Earth days. For Jupiter, nearly 12 Earth years. For Neptune, more than 164 Earth years. The farther a planet sits from its star, the longer its year, because it has a greater distance to travel, and because the gravitational pull holding it in orbit weakens with distance, allowing it to move more slowly. TOI-5205b completes one full orbit around its star in approximately 1.63 Earth days. Not 1.63 years, not 1.63 months, 1.63 days, 39 hours. A year on the forbidden planet is shorter than 2 of our days. By the time you have slept through tonight, woken, gone about your day, slept again, and woken a second time, TOI-5205b will have completed more than one full orbit of its star. It will have experienced an entire year in the time it takes you to live through a single Tuesday and Wednesday. This number, 1.63 Earth days, is not just remarkable in isolation. It is remarkable because of what it implies about where the planet must be sitting in relation to its star. The speed of an orbit and the distance from the central star are locked together by the laws of gravity in a relationship that admits no exceptions. A planet moves fast because it is close. It is close because gravity there is strong. It completes its orbit quickly because it has a short distance to travel and is moving quickly to do so. TOI-5205b orbits its star at a distance of approximately 2.5 million miles. In the context of human experience, 2.5 million miles sounds enormous. It is roughly 10 times the distance from the Earth to the Moon. It is a vast gulf of space by any human measure. But in the context of planetary orbits, in the context of the distances that typically separate planets from their stars, 2.5 million miles is extraordinarily small. It is, to put it in terms that may help calibrate the scale, roughly 1/10 of the distance between Mercury and our own Sun. Mercury is already the closest planet to the Sun in our solar system, so close that it was long considered the most inhospitable of the classical planets, a world of scorching days and freezing nights and temperatures extreme enough to melt lead on its sun-facing surface. Mercury orbits the Sun at an average distance of about 36 million miles. And even that is close enough to give it a surface temperature that averages around 167 degrees Celsius on the day side. TOI-5205b is 1/10 that distance from its star, not a little closer, 10 times closer than the closest planet to our own Sun. It hugs its host star with an intimacy that has no analog anywhere in our solar system, circling at a distance so small that if you place the star and planet in the same scale model as our solar system, the planet's orbit would barely be distinguishable from the surface of the star itself. This combination of characteristics, a gas giant enormous in mass, orbiting its star at extremely close range in a very short period, places TOI-5205b firmly within a category of exoplanets that has fascinated and puzzled astronomers since the first examples were discovered in the 1990s. This category is called hot Jupiters. Hot Jupiters are, as the name suggests, giant planets, Jupiter-class in their mass and size, that orbit their host stars at very close distances, producing very short orbital periods and, as a consequence, very high temperatures. The first confirmed hot Jupiter ever discovered, 51 Pegasi b, was detected in 1995 and caused a significant stir in the scientific community, precisely because nothing in our own solar system had prepared scientists to expect a Jupiter-sized world orbiting so close to its star. The theoretical models of the time had not predicted their existence in any significant numbers, and yet here they were, turning up in the data with a frequency that suggested they were not as rare as the models would have implied. Hot Jupiters remain, in some ways, the exotic celebrities of exoplanet science. They are relatively easy to detect. Their large size and close orbits make them produce strong signals in both the transit method and the radial velocity method that astronomers use to find planets around distant stars. And they are fascinating objects in their own right, representing conditions that have no equivalent in our own solar neighborhood. TOI-5205b is a hot Jupiter, but it carries an additional layer of strangeness beyond what most hot Jupiters bring to the table, because of the nature of its host star. Most known hot Jupiters orbit Sun-like stars, larger, warmer, more generous with their light. TOI-5205b orbits a red dwarf, a small, dim, cool star. And this combination, hot Jupiter around an M dwarf, is itself unusual, adding another dimension to the already considerable improbability of this world. Now let us talk about the shape of the orbit itself. When we picture planets moving around stars, there is often an unconscious assumption that the path is elliptical, stretched into an oval, with the star sitting off-center, the planet swinging close at one end and retreating to greater distance at the other. This is, in fact, how many orbits work. Earth's own orbit is slightly elliptical, though only mildly so. Our closest approach to the Sun, called perihelion, is about 3 million miles closer than our farthest point, called aphelion. The ellipticity of Earth's orbit is slight enough that it has no dramatic effect on our seasons. Some planets in our solar system have significantly more elongated orbits. Mercury's is notably elliptical, And many of the dwarf planets in the outer solar system have orbits that are dramatically stretched. And many exoplanets discovered around other stars have been found to follow elliptical paths of varying degrees of elongation. But TOI-5205b does not. Its orbital eccentricity, the measure of how far an orbit deviates from a perfect circle, is very close to zero. It moves in a nearly perfect circle around its star. The distance between the planet and its star at any point in the orbit is almost exactly the same as at any other point. The orbit is clean and regular and symmetrical, without the periodic variation in distance that an elliptical path would produce. This circular orbit is not an accident. It is, in all likelihood, the product of a process called tidal circularization, the same family of tidal forces that produces another of this planet's most extraordinary characteristics, and the one that may be the most viscerally striking of all the things we have learned about TOI-5205b. Because the planet orbits so close to its star, the star's gravity does not pull equally on all parts of the planet. The side of the planet that faces the star at any given moment is slightly closer to the star than the side that faces away, and gravity weakens with distance. So the near side of the planet experiences a slightly stronger gravitational pull than the far side. This difference, small in absolute terms, but significant when applied continuously over billions of years, creates what physicists call a tidal force. A stretching, squeezing influence that acts on the planet's material and, over immense timescales, gradually changes both the shape of the orbit and the rotation of the planet. Over billions of years, this tidal force has done something remarkable to TOI-5205b. It has slowed the planet's rotation, the spin that would otherwise give it a day-night cycle. The way Earth's spin gives us our familiar alternation of daylight and darkness, until the rotation is no longer an independent motion at all. The planet now rotates exactly once for every time it orbits the star. One rotation per orbit, one spin per year, which means that the same face of the planet always points toward the star, and the opposite face always points away. This condition is called tidal locking, and our own moon is the most familiar example of it in our solar system. The moon orbits Earth in exactly the same time it takes to rotate once on its axis, which is why we always see the same face of the moon from Earth, why the far side of the moon remained unknown to human eyes until spacecraft flew around it. The moon is tidally locked to Earth. TOI-5205b is almost certainly tidally locked to its star, and the consequences of this are extraordinary. Imagine a planet divided permanently and absolutely into two hemispheres, not by some accident of geography or climate, but by the fundamental geometry of its relationship with its star. One hemisphere, the day side, faces the star forever. It receives all of the star's light and heat continuously, without interruption, without the relief of nightfall, without the cooling that comes when a planet rotates away from its sun. Whatever temperature that hemisphere reaches under constant stellar irradiation, it maintains, always. The star never sets on the day side of TOI-5205b. The star has never set and never will. The other hemisphere, the night side, faces away from the star forever. It receives no direct starlight at all. It sits in permanent darkness, radiating whatever heat it contains outward into the cold of space, cooling and cooling without the warming that a rotation would bring. The star has never risen on the night side of TOI-5205b. It never will. Between these two extreme hemispheres, around the planet's equator, there is a region called the terminator, the line where eternal day meets eternal night. On a tidally locked world, This boundary is a permanent geographic feature. It runs as a ring around the planet, always in the same position relative to the star and to the planet's surface. On one side of it, endless baking light. On the other, endless dark cold. For a gas giant like TOI-5205b, the consequences of this are written in its atmosphere. The dayside atmosphere, heated continuously by the star, would likely be extraordinarily hot, temperatures potentially reaching thousands of degrees in the uppermost layers, driving enormous convective upwellings and powerful circulation patterns. The night side, starved of energy, is dramatically cooler. The temperature gradient between the two hemispheres drives massive atmospheric wind systems, planet-wide jet streams carrying heat from the day side toward the night side in an attempt to equalize the imbalance that can never quite be equalized. Hot Jupiters are known, from observations of other systems, to have wind speeds that can reach and exceed the speed of sound. The atmospheric dynamics of a tidally locked gas giant are among the most extreme environments that planetary science attempts to model. Now add to this the forces operating not just on the planet's atmosphere, but on its interior. The same tidal forces that circularize the orbit and lock the rotation also act on the planet's interior. As the star's gravity squeezes and stretches the planet, and as the planet's own rotation interacts with the gravitational field, the material inside the planet flexes and deforms slightly. This flexion generates heat, in the same way that a metal wire heats up when you bend it back and forth repeatedly. The process is called tidal heating. Tidal heating is responsible for some of the most dramatically active geology in our solar system. Io, the innermost large moon of Jupiter, is the most volcanically active body we have discovered, covered in erupting volcanoes, resurfaced continuously by lava flows, because it is squeezed and flexed by Jupiter's immense gravity as it orbits. The tidal forces on Io are so powerful that they keep its interior partially molten, driving a level of geological activity that has no equivalent on Earth. For TOI-5205b, the tidal forces are immense. The planet sits incredibly close to its star, and the star's gravity at that distance is enormously powerful. The interior of this planet is being continuously stressed and flexed, generating heat from within, even apart from whatever the star provides from without. This tidal heating contributes to the overall energy budget of the planet in ways that are not yet fully characterized, but are almost certainly significant. And there is a longer, slower consequence of these tidal forces as well. Over time scales of billions of years, tidal interactions between a planet and its star do not simply circularize the orbit and lock the rotation and then stop. They continue to operate. And one of the things they do gradually is cause the planet's orbit to slowly decay, to shrink. The same gravitational interaction that circularized the orbit and slowed the rotation also, over enormously long timescales, transfers energy between the planet's orbit and the star's rotation in a way that can cause the planet to spiral slowly, incrementally, almost imperceptibly inward. If this process operates over sufficient time on TOI-5205b, the planet may eventually spiral close enough to its star to be disrupted, torn apart by the star's tidal forces once it crosses what is called the Roche limit, the distance within which the star's gravity exceeds the planet's own self-gravity and the planet begins to disintegrate. This is not imminent. The time scales involved are billions of years, and the process is slow and uncertain, dependent on factors not yet precisely measured. But the possibility exists, a distant, unhurried fate in which the forbidden planet's impossible existence ends as it was begun, in defiance of simple expectation, consumed by the star that made it. And then there is the question of where TOI-5205b sits in relation to what astronomers call the habitable zone, the range of distances from a star within which liquid water could theoretically exist on the surface of a rocky planet. The habitable zone is not a fixed distance, but depends on the luminosity and temperature of the star in question. Around our own sun, the habitable zone spans from roughly 0.95 to 1.7 astronomical units, the region that includes Earth and extends partway to Mars. Around TOI-5205, a much dimmer and cooler star, the habitable zone sits much closer to the star, because a cooler star provides less warmth and a planet must orbit nearer to receive enough energy to maintain liquid water. Estimates place the inner boundary of TOI-5205's habitable zone at roughly 6 or 7 times the orbital distance of TOI-5205b, which means that TOI-5205b does not just miss the habitable zone. It is far inside its inner boundary. It orbits at a fraction of the distance at which even the most generous definition of habitability would begin. At its orbital distance, receiving the radiation it receives, TOI-5205b is a place where any water that may have ever existed would have been vaporized long ago. Not slowly evaporated or gently driven off, vaporized. Converted instantly and completely into steam and photo-dissociated by stellar radiation into its component atoms. There is no water on TOI-5205b. There is no liquid of any kind resting on any surface because there is no surface, and because the temperatures involved are incompatible with any of the forms that water takes in our experience. And yet the planet endures, hot and tidally locked and subject to immense internal forces, and slowly, perhaps, spiraling inward toward an eventual encounter with its star, it endures. It has endured for however long it has existed, billions of years, most likely, of these extreme conditions. Billions of years of permanent day on one hemisphere and permanent night on the other, of atmospheric winds blowing at speeds that dwarf anything in our own solar system, of tidal forces flexing its interior and slowly reshaping its orbit. It is, in every physical sense, a world of extremes. Nothing about its existence is moderate. Nothing about the conditions it experiences lies within the comfortable middle range of planetary environments. It occupies the far edge of what is possible, close to its star, large for its system, improbable in its formation, dramatic in its dynamics. And yet in all of this extremity, there is something almost calming about the regularity of it. The orbit is a perfect circle. The year is exactly 1.63 days, repeated again and again with the precise, unwavering consistency of clockwork. The same face always turned toward the star. The same face always turned away. The winds following the same eternal paths from day to night and back again. The tidal forces operating with a quiet, steady, geological patience that has no regard for urgency. There is a rhythm to it, an extreme and alien rhythm, but a rhythm nonetheless. A pattern that has been repeating since before our sun ignited, perhaps, since before life stirred in Earth's ancient oceans. A clock that ticks not in hours, but in the 1.63-day sweep of a gas giant around a red dwarf star, over and over, in the quiet dark of a constellation called the Little Fox. As you settle deeper into rest, let that rhythm be something to drift alongside. Slow and regular and vast. A year ending and beginning again every 2 days, 283 light years away. The star always in the same position as seen from the planet's frozen dayside. the night side always facing the cold and the dark and the stars beyond. The planet turning, or rather, not turning, perfectly still in its orientation, perfectly faithful in its circle. There is no better night to rest deeply than this one, and there is no simpler truth than the one the forbidden planet quietly embodies, that the universe has its own rhythms, its own cycles, its own patient and enormous timekeeping, entirely independent of our urgency or attention or understanding. It will keep orbiting, whether we are watching or not. Segment 5. Physical characteristics of the planet. There is a certain kind of knowledge that lives not in the mind, but in the body. The knowledge of weight, for instance. The felt sense of gravity pressing you into wherever you are resting right now. The comfortable heaviness of your own limbs settling into stillness. The knowledge of temperature, the particular quality of warmth that comes from being inside on a cool night. The way the air feels different in different seasons. The knowledge of substance, the difference between something solid beneath your feet and something that gives way, that offers no resistance, that has no bottom. These are the kinds of knowledge that connect us to the physical world in the most immediate and personal way. And they are precisely the kinds of knowledge that fail us, that have no foothold, when we try to imagine what it would mean to stand on, or rather within, a world like TOI-5205b. Because everything about the physical reality of this planet sits at the far edge of what our bodily intuition can reach. The weight is wrong. The temperature is wrong. The very idea of a surface is wrong. TOI-5205b is a place that does not accommodate human scale or human reference points. A world whose physical characteristics can be measured and described in numbers, but cannot be experienced in any direct way that our bodies would recognize. And so tonight, as we explore what this planet actually is, what it is made of, how massive it is, how dense, how hot, how structured, let us hold the numbers lightly, as invitations to the imagination rather than demands on it. Let each fact be a window rather than a wall, a way of glimpsing something vast and strange rather than a requirement to fully contain it. We begin with the most fundamental physical measurements, the mass and the radius, the two quantities that, together, tell us more about a planet's basic nature than almost anything else. TOI-5205b has a mass approximately 1.08 times the mass of Jupiter. It is, in other words, almost precisely Jovian in its mass, just slightly heavier than the largest planet in our own solar system. This number is striking in its near exactness. Not dramatically more massive than Jupiter, not dramatically less, essentially the same mass, within a few percent. If you were to place TOI-5205b alongside Jupiter on some cosmic scale, the two objects would nearly balance. This near equivalence in mass is part of what makes TOI-5205b so useful as a scientific object. Jupiter is the reference point, the standard by which gas giants are measured. It is the planet we know best, the one whose atmosphere we have sent probes into, whose moons we have photographed in extraordinary detail, whose dynamics we have studied for centuries. When we say that TOI-5205b is 1.08 Jupiters in mass, we are connecting it to this well-understood reference, saying that it belongs to the same physical category as the planet that anchors our understanding of gas giants. And the radius? TOI-5205b is approximately 1.03 times the radius of Jupiter. Again, almost exactly Jovian in its physical size. A sphere very nearly the same diameter as Jupiter, containing very nearly the same mass. Two planets, one in our own solar system, one 283 light-years away around a dim red dwarf, that are, by these basic measures, near twins of each other. But the similarity extends beyond just mass and radius. When you know both the mass and the radius of a planet, you can calculate its density, the amount of mass packed into each unit of volume. and the density of TOI-5205 becomes out to approximately 1.2 grams per cubic centimeter. This is, again, remarkably close to Jupiter's own density, which sits at about 1.33 grams per cubic centimeter. Both values are low, strikingly, almost paradoxically low if you are used to thinking of planets as rocky, dense, heavy things the way Earth is. For comparison, the density of water is exactly 1 gram per cubic centimeter. Earth's average density is about 5.5 grams per cubic centimeter, more than 4 times denser than water, because of all the iron and rock and silicate that makes up our planet's interior. TOI-5205b, with its density of 1.2 grams per cubic centimeter, is barely denser than water. It is, in essence, a vast sphere of material so lightly packed that if you could somehow find a body of water large enough to place it in, it would float, as would Jupiter. This extraordinary lightness is the signature of a gas giant's composition. These are not rocky worlds built from iron and silicate and mineral. They are built from hydrogen and helium, the lightest elements in the periodic table, the simplest atoms in the universe, the same elements that make up the overwhelming majority of all ordinary matter. A gas giant is, in the most fundamental sense, a concentrated sphere of the most abundant stuff in the cosmos. The atmosphere of TOI-5205b, which is not really separate from the planet itself in the way Earth's atmosphere is a thin shell around a solid body, but is rather the planet's body, the thing the planet is made of, is theorized to be composed overwhelmingly of hydrogen and helium. In this, again, it resembles Jupiter closely. Jupiter is roughly 75% hydrogen and 24% helium by mass, with everything else, water, ammonia, methane, and trace quantities of other compounds, making up only a small fraction of the total. TOI-5205b is almost certainly similar in broad composition, with the most abundant elements in the universe forming the bulk of its structure. But knowing what it is made of does not fully capture what it would be like. And to approach that, to reach toward any visceral sense of the conditions inside this planet, we need to think about what it means to have no solid surface. When we imagine a planet, there is an almost irresistible tendency to imagine a surface, a place where space ends and solid ground begins, a boundary you could stand on, look out from, feel beneath your feet. We can't help it. Every planet we have direct human experience of is like this. Earth has a surface. The Moon has a surface. Mars has a surface. Even the most alien rocky worlds we have studied have surfaces of one kind or another. TOI-5205b has none. This is not a matter of degree, not a planet with a surface hidden beneath thick clouds. Not a world where the ground is buried deep. There is no ground. There is no boundary between atmosphere and solid body. No line where gas gives way to rock or metal that you could theoretically descend toward and eventually reach. As you descended into the atmosphere of TOI-5205b, everything around you would simply become denser and hotter and more pressurized continuously without a rival. The gas would compress into liquid. The liquid would compress into states of matter that have no familiar names. Exotic high-pressure phases of hydrogen that exist nowhere on Earth except in laboratory experiments at extreme conditions. And at the very center, there may be a dense core of heavier material, rock, metal, ice under extraordinary compression. But that core is not a surface. It is a buried remnant, invisible and inaccessible beneath thousands of kilometers of increasingly extreme material. To descend into TOI-5205b would not be like descending to the floor of an ocean, where there is eventually a bottom. It would be like descending into a substance that continuously thickens and crushes around you, with no arrival, no bottom, no destination. The concept of where you would stand simply does not apply. And yet the concept of gravity does. and it applies with considerable force. At the upper boundary of TOI-5205b's cloud layers, the closest thing the planet has to a surface, the level at which atmospheric pressure matches a rough reference point that scientists use for gas giants. The gravitational pull is approximately 2.5 times stronger than Earth's. This is the gravity that would act on anything at the top of the planet's atmosphere. 2.5 times Earth's gravity is a deeply meaningful number if you try to inhabit it physically, even in imagination. It means that something weighing 100 pounds on Earth would weigh 250 pounds there. It means the effort required to lift your own body against that pull, to stand, to raise an arm, to turn your head, would demand 2.5 times more from your muscles than the same movements require here. Astronauts returning from extended stays in low gravity find Earth's gravity temporarily exhausting, their bodies struggling to readjust to conditions they evolved for. TOI-5205b's gravity would be immediately and profoundly crushing, not to the point of being instantly lethal for a human body, but to the point of making every physical action a significant effort. Of course, none of this matters practically, because no human body could approach TOI-5205b for entirely separate reasons, beginning with the temperature. The equilibrium temperature of TOI-5205b, the baseline temperature that results from the balance between the energy the planet receives from its star and the energy it radiates back into space, is estimated at approximately 735 Kelvin. Converting to more familiar scales, this is roughly 462 degrees Celsius, or approximately 863 degrees Fahrenheit. Let those numbers sit for a moment. 863 degrees Fahrenheit. This is not a temperature that falls within any range of human experience. It is not the temperature of a hot summer day, or a desert at noon, or a sauna, or even an industrial oven. It is hotter than the surface of Venus, the hottest planet in our solar system, at around 465 degrees Celsius. And Venus is notoriously extreme, a world of crushing pressure and acid clouds and temperatures hot enough to melt spacecraft in minutes. At 735 Kelvin, the atmosphere of TOI-5205b is hot enough to melt metals that we think of as functional at high temperatures. Zinc melts at around 693 Kelvin. Lead melts at around 601 Kelvin. At 735 Kelvin, both of these metals would be liquid, pooling and flowing the way water pools and flows in familiar experience, but made of metal. Any object made of zinc or lead that somehow found itself in the upper atmosphere of TOI-5205b would not remain solid. It would become liquid. It would drip. And yet, and this is one of the quietly extraordinary ironies embedded in the physical reality of this planet, 735 Kelvin is, in the context of a class of objects to which TOI-5205b belongs, relatively cool. Hot Jupiters come in a wide range of temperatures. The most extreme examples, those orbiting very close to large, bright, hot stars like our own sun or hotter, can reach equilibrium temperatures of 2000 Kelvin, 2500 Kelvin, even beyond 3000 Kelvin. At those temperatures, the atmosphere of a gas giant begins to behave in ways that bear no resemblance to anything in our own solar system. Molecules are torn apart by the heat. Metals vaporize and circulate in the atmosphere as vapor, condensing on the cooler night side into metallic rain. Liquid iron falling from clouds, liquid titanium, liquid aluminum. These are the so-called ultra-hot Jupiters, and they represent a class of objects so extreme that the very chemistry of their atmospheres is altered at a fundamental level. At 735 Kelvin, TOI-5205b sits below this ultra-hot threshold. It is hot enough to melt lead and zinc, hot enough to exceed the melting point of many metals, hot enough to be utterly lethal to any biology we know of, but not hot enough to vaporize iron. not hot enough to dissociate water vapor into its component atoms in the uppermost layers of the atmosphere. In the classification of hot Jupiters, it occupies a kind of middle ground, extreme by any absolute measure, but relatively temperate by the standards of its category. This relative moderation in temperature has implications for what the atmosphere of TOI-5205b might be like in terms of its chemistry. At temperatures below about 1000 Kelvin, certain molecules can remain stable. Water vapor, for instance, though not liquid water. Methane, at lower levels of the atmosphere, where temperatures drop with depth. Carbon dioxide. These are molecules whose spectral signatures astronomers look for when studying exoplanet atmospheres, because they can be detected from a distance using instruments like the TOI-5205b is, in fact, one of the targets that makes astronomers most excited about atmospheric characterization, and we will explore that in more depth in a later segment. For now, simply hold the idea that this planet's temperature, while utterly hostile by any human standard, is modest enough to preserve molecular structure in its atmosphere in ways that the hottest hot Jupiters cannot. But there is one more physical characteristic of this planet that deserves careful attention, and it follows directly from the temperature. It is a consequence of all that heat, a consequence that reshapes the planet's physical structure in a measurable and somewhat counterintuitive way. The intense heat pouring into TOI-5205b from its nearby star causes the planet's outer gaseous layers to expand. The gas, receiving enormous amounts of energy, heats up, and hot gas occupies more volume than cool gas. The atmosphere literally inflates. It puffs outward, extending farther from the planet's center than it would if the same planet were orbiting at a cooler, more distant position from its star. This phenomenon is called atmospheric inflation, and planets that exhibit it are sometimes informally described as being puffed up. The practical effect of atmospheric inflation is that a planet can have a larger radius than you would predict from its mass alone. A gas giant of a given mass, sitting close to a hot star, will be physically bigger, will span a wider diameter, than an identical gas giant sitting far from any star. The density comes out lower, the radius comes out larger, because the atmosphere has been heated and expanded by the energy it continuously receives. TOI-5205b shows signs of this effect. Its radius is slightly larger than you might naively expect for a planet of its mass. The outer layers of its atmosphere are extended, stretched outward by the heat of its host star. The planet is, in a physical sense, bloated, not by any exotic chemistry or special composition, but simply by the thermodynamic consequence of being very close to a star. This puffing has a further consequence that connects forward to the planet's future. An expanded atmosphere has a larger cross-section. It extends further into space and is therefore more easily eroded by the stellar wind, the stream of energetic particles that flows continuously from the star's surface. Over geological timescales, this atmospheric erosion, called photoevaporation, can slowly strip mass from the outer layers of a close-in gas giant, contributing to the slow transformation of the planet's structure over billions of years. For TOI-5205b, the rate of this mass loss is an open question, but it is almost certainly occurring at some level. The planet is being very slowly unwrapped by its star, layer by outermost layer, year by year, in quantities so tiny they are unmeasurable over any human timescale, but significant over the billions of years the planet has already existed and the billions more it will continue to orbit. And so we arrive at the full picture of what TOI-5205b is, physically speaking. A world 1.08 times the mass of Jupiter and 1.03 3 times its radius, a near twin in these fundamental measurements. A world with a density barely exceeding that of water, composed overwhelmingly of the lightest elements in the universe. A world with no solid surface, no boundary, no ground, only the continuous thickening of a gas that becomes liquid, that becomes something stranger still, deeper inside. A world where the gravity at the cloud tops would press down on anything in it with 2.5 times the force of Earth gravity. A world baking at temperatures that melt metals, and yet considered relatively cool within its category. A world whose atmosphere has been puffed outward by heat, slowly being eroded at its outermost edges by its star's relentless wind. It is a world of superlatives, of extremes, of conditions that strain the imagination. And it is, in spite of all of this, or perhaps because of it, one of the most physically fascinating objects that modern astronomy has given us to think about. The numbers are extraordinary, but there is something almost restful in them once you let them settle. Mass and radius and density and temperature. These are clean measurements, precise and well-defined. They do not ask anything of you. They simply describe. They paint a portrait of a place that does not need your presence to exist, that has been exactly what it is for billions of years, quietly being a gas giant in the constellation of the Little Fox, with no knowledge of and no regard for the small blue planet far away, whose inhabitants would one day measure it and name it and call it forbidden. Let the portrait rest in your mind now, loosely. A vast, slowly puffing sphere of hydrogen and helium. The color of its clouds a mystery, the depth of it beyond imagining, warm by its own standards and permanent and real. Segment 6, the discovery process. There is something deeply human about the act of finding something that was always there. The forbidden planet did not come into existence when we discovered it. It has been orbiting its small red star for what are almost certainly billions of years, circling, patient, and indifferent, through all of the time that life on Earth was slowly assembling itself from simple chemistry into something complex enough to eventually look up at the sky and wonder what was out there. It was there when the first human beings made their fires and watched the stars wheel overhead and told each other stories about what those lights might be. It was there when the first telescopes were built and turned upward. It was there through all the centuries of astronomy that preceded the technology capable of detecting it. And then one day, through the accumulated effort of spacecraft and software and ground-based instruments and the patient, careful work of scientists across multiple countries and in discovery in modern astronomy is rarely a single moment. It is rarely the dramatic, crystalline instant of a lone scientist at a telescope suddenly seeing something new and knowing immediately what it is. It is more often a process, layered, methodical, collaborative, built from multiple independent confirmations and careful checks, and the slow accumulation of evidence until the signal becomes undeniable. It is, in this sense, more like the gradual emergence of understanding than the sudden flash of revelation. The discovery of TOI-5205 followed exactly this kind of process, and tracing it from the first automated flag in a satellite's data stream to the published paper in a peer-reviewed journal is its own kind of story. A story about how we find things we cannot see directly, how we know things we cannot touch, how science works in practice when the object of study is 283 light years away, and the only information we have arrives as light. The story begins in space. Specifically, it begins with NASA's TESS spacecraft, the Transiting Exoplanet Survey Satellite, whose acronym gave TOI-5205 be the first 2 letters of its name. TESS was launched in April of 2018 and placed in a unique elliptical orbit around Earth that takes it far enough away to escape the interference of Earth's radiation belts, but close enough to maintain reliable communication with ground stations. From this orbit, TESS watches the sky, staring at individual patches of stars for extended periods and recording the brightness of every star in its field of view with extraordinary precision. The instrument at the heart of TESS is relatively simple in concept, though sophisticated in execution. It is essentially a very precise camera, or rather, for cameras working together, designed to measure the brightness of stars with enough accuracy to detect the tiny, fleeting dimming that occurs when a planet passes in front of a star, as seen from our direction in space. This technique is called the transit method, and it has become the most productive method ever developed for finding planets around distant stars. The transit method works by exploiting the geometry of planetary orbits. When a planet orbits its star in a plane that happens to be aligned with our line of sight, when from our perspective here in the solar system, the planet's path carries it across the face of its star, it briefly blocks a small fraction of the star's light. The star appears slightly dimmer for the duration of the transit, and then returns to its normal brightness when the planet has passed. This dimming, called a transit signal, repeats every time the planet completes an orbit, regularly, predictably, with a timing that reflects the planet's orbital period. For most planets, this dimming is extremely small. Earth transiting the Sun, as seen from a distant star, would block only about 0.008% of the Sun's light, a variation so tiny that detecting it requires instruments of exceptional precision. TESS is designed to detect variations at this scale and smaller, which is why it can find planets that no human eye and no previous generation of instrument could have identified. But TOI-5205b is not like most planets. TOI-5205b is a gas giant orbiting a very small star, and the transit signal it produces is not tiny. When a planet 1 Jupiter radius in size crosses the face of a star only slightly larger than Jupiter itself, when the occulting disk is nearly as large as the disk it is occulting, the fraction of light blocked is not a fraction of a percent. It is enormous. A single transit of TOI-5205b blocks a significant fraction of its host star's total light, a dip so deep and so dramatic that when TESS's automated algorithms encountered it in the data, they flagged it not as a planet signal, but as something else entirely. The signal was so massive that the software initially classified it as a potential binary star system. This is a significant and telling detail about how discovery actually works in practice. Automated systems, the algorithms that process the enormous streams of data from telescopes like TESS, are trained on patterns. They learn to recognize what different kinds of signals look like. And a signal as deep as the one TOI-5205b produced, a dimming that large, that regular, that pronounced, did not match the expected pattern of a planetary transit in the minds of the algorithms. It matched instead the pattern of a binary star system, a pair of stars orbiting each other, where the dimmer star periodically passes in front of the brighter one, blocking a significant portion of its light. Binary star systems are extremely common. Roughly half of all stars similar to our Sun exist in binary or multiple systems, orbiting gravitational partners. And when one star in a binary transits its partner, it can produce exactly the kind of deep, regular dimming that TESS saw in the data for TOI-5205. So the automated system did exactly what it was designed to do. It flagged the signal and categorized it according to the pattern it most resembled. This is not a failure of the system. It is the system working correctly. Automated processing cannot make the subtle judgments that require additional context and investigation. Its job is to sort the overwhelming flood of data into categories and flag the anomalies for human attention. And flag it did. ensuring that this particular signal, this particular star, this particular pattern was not lost in the noise, but was passed forward to the scientists who could look more carefully. Among those scientists was a team led by Shubham Kanoda, an astronomer at the Carnegie Institution for Science, an organization with a long and distinguished history in American science, headquartered in Washington, D.C., with research facilities spread across the country. Kanoda and his team were specialists in M-dwarf planetary systems, the very category of star system in which TOI-5205 sits, which made them precisely the right people to examine what Tess had flagged. The task before them was fundamental and deceptively simple to state. Determine whether the signal Tess had detected was a planet or something else. Prove that a gas giant was orbiting this small red star rather than a binary stellar companion, producing a superficially similar light curve. Gather enough independent evidence from enough independent sources to bring the claim to the standard of certainty that a peer-reviewed scientific publication demands. This is the work of confirmation, and it is painstaking work, not dramatic in the way that popular imagination tends to picture science, not a moment of sudden revelation, but a methodical accumulation of data points from multiple instruments, each one adding another thread to the weave of evidence until the picture is complete and solid. The first and most essential tool in confirming whether a transit signal belongs to a planet or a binary star companion is something called the radial velocity method. It is sometimes described informally as the Doppler wobble method, and the image that name conjures of a star being gently tugged back and forth by the gravitational pull of something orbiting it is actually quite accurate. Every object with mass exerts a gravitational influence on everything around it. Planets are often thought of as the passive subjects of their star's gravity, held in orbit, pulled around, controlled. And this is true, but the planet's own gravity acts on the star as well. A large planet, especially one as massive as TOI-5205b, tugs on its host star as it orbits, causing the star to trace a small circle or ellipse of its own around the shared center of mass of the system. For most planets around most stars, this stellar motion is extremely small. Our own Jupiter causes our Sun to wobble at a speed of about 12 meters per second, roughly equivalent to a fast sprint. But the motion is real, and because of the Doppler effect, the same physical phenomenon that causes the pitch of a passing ambulance siren to rise as it approaches and fall as it recedes. This small stellar motion changes the wavelength of the light we receive from the star in a measurable way. When the star's motion carries it slightly toward us, the light it emits is compressed slightly, shifted toward bluer wavelengths. When the motion carries it slightly away, the light is stretched slightly toward redder wavelengths. By measuring this shift in the star's spectrum with great precision, astronomers can determine the speed of the stellar wobble. And from that speed, they can calculate the mass of whatever object is causing it. This is the key distinction between a planet and a binary stellar companion. A stellar companion, even a dim, small star, would cause a much larger wobble than a planet. The mass difference between even the smallest stars and the largest planets is enormous, and this difference shows up clearly and unambiguously in the radial velocity signal. If the object causing the transit is a star, the wobble will be large. If it is a planet, the wobble will be small. The math is clear and the distinction is usually unambiguous. To make this measurement for the TOI-5205 system, Kanodia's team turned to an instrument called the Habitable Zone Planet Finder, or HPF, a spectrograph installed at the Hobby-Eberly telescope at the McDonald Observatory in the Davis Mountains of West Texas. The Hobby-Eberly telescope is one of the largest optical telescopes in the world, with a primary mirror spanning about 10 meters. The HPF spectrograph attached to it is designed specifically for measuring the radial velocities of M-dwarf stars, a technically challenging task because M-dwarfs emit most of their light in the infrared and require instruments optimized for that part of the spectrum rather than the visible light that most spectrographs are built to measure. The HPF, in other words, was purpose-built for exactly this kind of work. It was designed by astronomers who understood that red dwarf stars were going to be crucial targets in the search for exoplanets, and who recognized that the standard visible light spectrographs used for sun-like stars were not ideally suited to the dimmer, redder light of M-dwarfs. The instrument is extraordinarily precise, capable of measuring Doppler shifts corresponding to stellar motions of just a few meters per second, far smaller than the widths of the spectral lines it measures, through a combination of engineering sophistication and calibration techniques that represent some of the most advanced instrumentation in ground-based astronomy. When the HPF measured the radial velocity of TOI-5205, it found a wobble, and the amplitude of that wobble, the speed of the stellar motion it detected, was consistent with a planet, not a stellar companion, not a binary star, a planet more than 1,000 times less massive than any star. The mass calculation that came from that wobble measurement pointed to an object in the range of Jupiter's mass, confirming that whatever was causing the deep transit signal in TESS's data was not a stellar body, but a planetary one. But one line of evidence, no matter how strong, is rarely enough. Science demands redundancy. It demands that conclusions be supported by multiple independent methods, that the possibility of systematic error in any single instrument or technique be ruled out by cross-checking against different instruments using different principles. And so the confirmation effort continued. A second piece of the puzzle came from the Apache Point Observatory in New Mexico, home to the 3.5-meter telescope, and the instrument known as Arctic, the Astrophysical Research Consortium Telescope Imaging Camera. Arctic is a high-sensitivity imager designed to capture precise photometric measurements of brightness, with excellent spatial resolution. The Arctic instrument was used to observe a transit of TOI-5205b directly from the ground, capturing the dimming of a star as the planet crossed its face and measuring the precise timing of that transit. When it began, when the planet was fully in front of the star, when it ended. This ground-based transit timing served multiple purposes. It allowed the team to confirm that the transit signal was real, that it appeared consistently and at the predicted times when observed from an entirely independent facility. It also provided additional constraints on the geometry of the transit, the size of the blocking object relative to the star, the depth of the dimming, the shape of the light curve as the planet moved across the stellar disk. The shape of a transit light curve carries information. The way the brightness drops at the start of a transit and recovers at the end, the depth of the flat bottom minimum, the duration of the event, all of these features, taken together, constrain the physical properties of both the planet and the star. A planet produces a characteristically shaped transit. A stellar companion, even a small one, often produces a transit with subtly different characteristics. Ground-based imaging like Arctic's can detect these differences, adding another layer of discrimination between planetary and stellar scenarios. And there was a further advantage to having ground-based observations from a high spatial resolution instrument, ruling out the possibility of a background star. One of the persistent challenges in transit astronomy is the possibility that the dimming signal attributed to a transit is actually caused not by a planet orbiting the target star, but by an entirely separate background binary star system that happens to lie in the same direction on the sky, and whose eclipses are blended with the light of the target star in a way that mimics a transit. High-resolution ground imaging can check for the presence of nearby stars that might contaminate the signal, ensuring that the transit is genuinely associated with the intended target rather than an unrelated coincidence of alignment. With the Arctic confirmation of the transit timing and depth, and the HPF confirmation of the planetary mass through radial velocity, the evidence had accumulated to the point where the team could be confident. What tests had found, what the algorithms had initially miscategorized as a potential binary, was in fact a planet, a gas giant, a hot Jupiter orbiting a small red dwarf at an orbital period of 1.63 days. The entire effort required not just two instruments in two locations, but a large international team of astronomers, specialists in different aspects of M-dwarf stellar physics, in spectrographic techniques, in transit photometry, in planetary formation theory, pooling their expertise to assemble a complete and defensible picture of what had been found. This is the normal texture of modern astronomical discovery. Not a lone genius at a telescope, but a distributed collaboration of specialists, each contributing the particular knowledge and instrumental access that their piece of the puzzle requires. The resulting paper, authored by Kanoda and the full team of collaborators, was submitted to and peer-reviewed by the Astrophysical Journal Letters, one of the most respected journals in astronomy, a publication with a long history of hosting significant exoplanet discoveries. Peer review means that the paper was scrutinized by independent expert astronomers who had no involvement in the discovery and whose role was to evaluate whether the methods were sound, the data were correctly analyzed, the conclusions were justified by the evidence. This process, sometimes slow, sometimes frustrating, occasionally contentious, is one of the most important quality control mechanisms in science. It does not guarantee that published results are correct, but it substantially raises the bar of rigor that must be cleared before a claim reaches the scientific literature. The paper passed that scrutiny. The discovery was published in 2023. TOI-5205b entered the scientific record as a confirmed exoplanet, the forbidden planet, officially documented, peer-reviewed, and placed in the growing catalog of worlds we have found beyond our solar system. There's something genuinely moving about the trajectory of this discovery if you follow it from beginning to end. It begins with a satellite in orbit around Earth, silently measuring the brightness of hundreds of thousands of stars with the patient precision of a machine. It passes through an automated algorithm, making a reasonable but incorrect classification, flagging something unusual and passing it forward rather than dismissing it. It moves through the hands and minds of a team of scientists on multiple continents, each bringing their specialized knowledge and their particular instrument to bear on a single question. It travels to the high desert of West Texas and the mountains of New Mexico, to two telescopes aimed at the same small star in the constellation of the Little Fox. And it arrives, finally, in the pages of a journal, a permanent record of something found, something confirmed, something added to the total of what humanity knows about the universe it inhabits. All of this effort, all of this instrumentation, this expertise, this careful cross-checking and collaboration and peer review, all of it directed at a single small point of light in the sky, a point so faint it cannot be seen with the naked eye, a star less than half the size of our own sun, 283 light-years away. And the thing orbiting that star, the planet that should not exist, that broke the models, that sent scientists back to their equations, the thing that started all of it was a shadow, a tiny, repeating dimming of an already faint light, noticed by a machine, passed to a human, investigated with care, and ultimately recognized for what it was. The universe hid it in plain sight, in the data, in the light that had been traveling for nearly 3 centuries before arriving at our instruments. And we found it anyway. Not because it wanted to be found, not because it announced itself, but because we built the tools to look and had the patience to look carefully. That, at its heart, is what discovery is. Not revelation handed down, not accident stumbled upon, but patient, methodical, collaborative reaching toward the edge of what our instruments can detect, toward the limit of what our understanding can interpret, toward the faint and distant things that the universe contains whether we notice them or not. The forbidden planet was always there. We simply learned, finally, how to see it. Let that thought settle into the quiet with you. The idea that the universe is full of things waiting to be found, not hiding, not revealing, simply existing, and that the finding is something we do slowly and carefully and together, one careful measurement at a time. There is no urgency in any of it. The stars are patient. The data will still be there tomorrow. The planet will still be orbiting. The star will still be dimming and brightening, 283 light years away, whether anyone is watching or not. Segment 7, Observational Quirks and Transit Metrics. There is a particular kind of beauty in measurement, not the dramatic beauty of a sunrise or a storm or a landscape stretching to the horizon, but a quieter, more intellectual kind of beauty. The beauty of a number that is exactly right. The beauty of a signal that arrives clean and clear through the noise, that says something precise and unambiguous about the world. The beauty of a graph that shows, in a simple curve, the shadow of a world 100 light years away. This is the beauty that astronomers encounter when they look at the data from TOI-5205b, not the visual spectacle of the planet itself. We cannot see it directly, cannot photograph it the way we photograph the planets of our own solar system, cannot resolve it as anything more than an inference from the behavior of its star. But in the numbers, in the measurements, in the shape of the signal it leaves in the data, there is something genuinely striking. Something that stands out from the tens of thousands of other exoplanet signals in the accumulated catalogs of modern astronomy and announces itself as exceptional. Tonight, we are going to sit with those measurements, not in a dry or technical way, but slowly, carefully, letting each one unfold into something you can actually imagine, something you can hold in your mind as a real physical picture of what is happening in a star system 283 light years away. We begin with the most fundamental observational fact about TOI-5205b, the number that more than any other single measurement captures why this planet is so striking as an observational target. When TOI-5205b transits its star, when it passes across the face of TOI-5205 as seen from our direction in space, it blocks approximately 7% of the star's total light. 7%. Let that number settle for a moment before we put in context. 7% of a star's light blocked by a single planet. A dimming that, if you were watching TOI-5205 with a sufficiently precise instrument, would be immediately and dramatically apparent. The star would visibly, measurably, substantially darken as the planet moved in front of it, and then return to its full brightness, reduced by nearly 1/14 of its total output for the duration of the transit. In the world of exoplanet detection, this is an extraordinary number. Transit signals, the dips in stellar brightness caused by a planet crossing the star's face, come in a wide range of depths. Earth-sized planets transiting sun-like stars produce signals measured in parts per million. Dimmings, so tiny they require the finest space-based instruments to detect it all. Signals that are buried in noise and require careful statistical analysis to pull out. Even large, hot Jupiters transiting sun-like stars typically produce transit depths of around 1%, still demanding careful measurement, but far more robust than the signals of smaller planets. 7% is, by the standards of the field, enormous. It is one of the deepest exoplanet transit signals ever recorded, not the deepest ever measured in absolute terms. There are a handful of other systems involving very small stars and relatively large planets that approach or exceed this depth, but deep enough to rank among the most extreme transit events in the entire catalog of known exoplanets. Deep enough that when the TESS algorithms first encountered it, they questioned whether something other than a planet could be responsible. To calibrate what 7% means, it helps to compare it to something we can calculate from our own solar system. If an alien civilization somewhere in a distant star system happened to be watching our sun from a direction that placed them roughly in the plane of our solar system, and if Jupiter happened to be transiting the sun as seen from their perspective, what signal would they detect? Jupiter is enormous. It is the largest planet in our solar system, more than 11 times the diameter of Earth, massive enough to contain more than 1,300 Earths by volume. It is, by any ordinary measure, a giant. And yet when you calculate the fraction of the sun's disk that Jupiter would cover during a transit, when you compare Jupiter's area to the sun's area, the answer comes out to just under 1%, roughly 0.9 to 1%. Jupiter blocking 1% of the sun's light. TOI-5205b blocking 7% of TOI-5205's light. The difference between these two numbers, between 1% and 7%, is almost entirely a consequence of one fact. The star that TOI-5205b orbits is dramatically smaller than our sun TOI-5205 is only slightly larger than Jupiter itself. And when a planet nearly the size of Jupiter transits a star barely larger than Jupiter, the fraction of the star's disk that the planet covers is not a small fraction. It is a substantial fraction, roughly 1/14 of the total stellar disk area, which is where the 7% comes from. This creates a visual situation that has no parallel in our own solar system, and that is when you try to imagine it genuinely strange and striking. An observer in the TOI-5205 system, somehow positioned to watch the transit happen in real time, would see something that our entire history of watching planets transit our own sun has not prepared us for. They would see a disk crossing the face of the star that is not a small spot, not a dark, but drifting slowly across a vast bright surface, but a circle nearly as large as the circle of the star itself. The planet, from this perspective, would appear almost the same size as its sun. Two disks nearly matched in apparent diameter, one the burning face of the star, one the dark silhouette of the planet moving across it. In the history of human observation of solar system transits, the transits of Mercury and Venus across our sun, which have been observed and scientifically exploited since the 17th century, the transiting planet has always appeared as a small, sharp-edged disk against the much larger and more brilliant face of the sun. The disproportion has always been obvious and dramatic. Mercury is a tiny black dot. Even Venus, the largest object we ever see transiting our sun, covers less than 1/10 of 1% of a solar disk. The sun is always overwhelmingly larger. But in the TOI-5205 system, this disproportion nearly vanishes. the planet and the star approach each other in apparent size. The transit is not the passage of a small, but something closer to the partial eclipse of one near equal by another. If you could stand in that system and watch the transit with your eyes, it might look less like a planet crossing a star and more like something that simply should not be the relationship between a star and a planet, which is perhaps fitting for a world called the Forbidden Planet. Now, the transit does not last long. Given that the planet is orbiting at a distance of only 2.5 million miles, moving at a very high orbital velocity to complete its 1.63-day year, and given that the star it is crossing is physically small, the transit event, from the first moment the planet's edge touches the star's limb to the final moment it clears the opposite edge, lasts approximately 1.7 hours. 1 hour and 42 minutes. Just over 100 minutes. In the span of a feature film, the Forbidden Planet completes its transit of its star. This is a short transit by exoplanet standards, which might seem counterintuitive given how dramatic the transit depth is. But transit duration is determined primarily by two things: how fast the planet is moving and how large the star is. TOI-5205b moves very fast. It has to complete an orbit in 1.63 days, and the star is small. Together, these factors mean the planet crosses the stellar disk quickly, even though the fraction of the disk it covers is large. The transit is deep because the star is small relative to the planet. The transit is short because the planet is fast and the star is small. The combination, a deep, short transit, creates a very distinctive shape in the light curve. A light curve is a graph that plots the brightness of the star over time, and for a transiting planet, it has a characteristic form. A flat baseline representing the star's normal brightness, a brief downward slope as the planet moves onto the stellar disk, a flat bottom representing the period of full transit when the planet is entirely in front of the star, another brief upward slope as the planet moves off the disk, and then a return to the baseline. This is the classic transit light curve shape, the U-shaped valley that exoplanet astronomers encounter in their data. For TOI-5205b, this U-shaped valley is not subtle. It is deep, dropping 7% below the baseline, and its flat bottom is relatively narrow in time, reflecting the short 1.7-hour transit duration. The walls of the U are steep, representing the rapid ingress and egress of a fast-moving planet crossing a small star. The overall shape is clean and clear and unmistakable. When Kanodia's team plotted the light curve of TOI-5205b, the transit signal was not something that required statistical squinting or careful noise filtering to perceive. It was simply there, bold and obvious. A valley in the brightness record that announced the planet's presence with more confidence than almost any other transit signal in the exoplanet catalog. This clarity, this strong, deep, clean signal, is described in scientific terms as a high signal-to-noise ratio. Signal-to-noise is one of the most fundamental concepts in all of observational science. Any measurement contains two components: the signal you are trying to detect and the noise, the random fluctuations, the instrumental errors, the background variations that are always present in real data and that can obscure or mimic the signal you are looking for. A high signal-to-noise ratio means the signal is large relative to the noise. It stands out clearly. It is unambiguous. It does not require elaborate statistical techniques to separate from the background. For most exoplanet transit signals, especially those of small, Earth-like planets around sun-like stars, signal-to-noise is a constant challenge. The signal is tiny and the noise is comparatively large, requiring many repeat observations, sophisticated analysis, and careful attention to potential confounding factors. For TOI-5205b, the transit is so deep, 7%, compared to fractions of a percent for most exoplanets, that the signal-to-noise ratio is excellent. The planet's presence in the data is not inferred or extracted. It is obvious. The data is clean. The transit is clear. The measurement is robust. This high signal-to-noise ratio has an enormously important practical consequence. It means that TOI-5205b is an exceptional target for one of the most powerful and scientifically valuable techniques in exoplanet science: transmission spectroscopy. Transmission spectroscopy is the method by which astronomers can study the atmosphere of an exoplanet, the composition of its gases, the presence of specific molecules, the temperature structure, the cloud layers. It exploits the fact that during a transit, a small fraction of the starlight does not simply pass around the planet, but passes through the planet's atmosphere. The thin annular ring of gas that extends beyond the planet's solid or liquid body into space. As this light filters through the atmosphere, different molecules in the atmosphere absorb different specific wavelengths of light. Water absorbs certain wavelengths. Carbon dioxide absorbs others. Methane, ammonia, and various other compounds each have their own characteristic absorption signatures. This selective absorption leaves fingerprints, specific wavelengths that are slightly dimmer during transit than they would be without an atmosphere. And by carefully comparing the star's spectrum during transit to its spectrum outside of transit, astronomers can detect and identify these fingerprints. Transmission spectroscopy is, in essence, a way of reading the chemistry of a distant world through its shadow in starlight. It is one of the most remarkable scientific techniques ever developed, allowing us to learn what an atmosphere is made of from a distance of hundreds of light years, using only the light that an alien planet filters as it passes in front of its sun. The quality of transmission spectroscopy data depends critically on the depth of the transit signal. A deeper transit means more atmospheric absorption signal to detect, a larger difference between in-transit and out-of-transit spectra, a stronger and cleaner atmospheric fingerprint. And this is where TOI-5205b's 7% transit depth becomes not just a measurement curiosity, but a genuinely valuable scientific asset. Its transit is so deep, the signal-to-noise ratio so favorable, that the atmospheric signal it produces during transmission spectroscopy observations is correspondingly large. Atmospheric features that would be buried in noise for a shallower transit are accessible, detectable, readable in the TOI-5205b data. The James Webb Space Telescope, the most powerful space telescope ever built, launched in December 2021 and fully operational since 2022, has been designed with precisely this kind of observation in mind. Its infrared sensitivity, its exceptional spectral resolution, and its position in space far from Earth's own absorbing atmosphere make it ideally suited to transmission spectroscopy of exoplanets. And TOI-5205b, with its deep transit, its relatively bright host star for an M-dwarf system, and its interesting position in the parameter space of gas giants around small stars, makes it a compelling target for exactly this kind of James Webb observation. We will explore what those observations might reveal and what they have already begun to reveal in a later segment. For now, the important thing to carry forward is this: the very property that made TOI-5205 be so anomalous and so puzzling as a theoretical object, its large size relative to its small star, is the same property that makes it so scientifically useful as an observational one. The same extraordinary size ratio that breaks the planetary formation models is what creates the exceptional transit depth that makes this planet one of the best atmospherically accessible gas giants known to science. It is as if the universe arranged not only for something impossible to exist, but for that impossible thing to be optimally placed for us to study it. There's one more observational technique worth exploring tonight. One that is somewhat more subtle than the blunt power of a 7% transit depth, but that carries its own elegant scientific value. It is called the Rossiter-McLaughlin effect, and it gives astronomers a way to measure something that would otherwise be essentially impossible to determine from a distance: the alignment between the planet's orbital plane and the star's own rotational equator. Stars spin. Our own sun rotates on its axis approximately once every 25 days at its equator. TOI-5205 rotates as well, likely more slowly, since the rotation of M dwarfs tends to decrease with age as the star loses angular momentum over time. And as the star rotates, one side of it is moving toward us, its light slightly blue shifted by the Doppler effect, while the other side is moving away from us, its light slightly red shifted. During a transit, as the planet moves across the face of the star, it sequentially covers different parts of the stellar disk. If the planet crosses the star in alignment with the star's rotational equator, moving from the side of the disk that is rotating toward us toward the side that is rotating away, it first covers some of the blue shifted light and then covers some of the red shifted light. This creates a characteristic, subtle distortion in the star's measured radial velocity during transit, a slight anomalous blue shift as the planet covers the receding side, followed by a slight anomalous red shift as it covers the approaching side, or vice versa depending on the direction of transit. This distortion is the Rossiter-McLaughlin effect, named for the two astronomers who independently studied it in the early 20th century. By measuring this effect during a transit of TOI-5205b, astronomers can determine whether the planet's orbit is aligned with the star's equator, as planets in our own solar system are, broadly speaking, aligned with the sun's equatorial plane, or whether the orbit is tilted at an angle. This alignment information is scientifically interesting because it constrains the history of the system. A planet that formed in a well-behaved disk and migrated inward gradually tends to arrive at a short-period orbit with its orbital plane aligned with the stellar equator. A planet that was scattered into its current orbit by gravitational interactions with other bodies may arrive misaligned, orbiting at a steep angle to the star's equator, or even in a retrograde direction. For TOI-5205b, this measurement, if it can be made with sufficient precision, could shed light on the migration history of the planet. Did it form far from the star and spiral inward gracefully? Was it hurled to its current orbit by some gravitational drama in the system's past? The Rossiter-McLaughlin effect offers a way to distinguish between these scenarios, adding another layer of constraint to the already rich and puzzling story of how this planet came to be where it is. And here again, the deep transit of TOI-5205b works in the astronomer's favor. The Rossiter-McLaughlin effect is most easily measured when the transit itself is deep, because a deeper transit means the planet covers more of the stellar disk, producing a larger anomalous velocity signal. 7% transit depth means a large Rossiter-McLaughlin signal, more accessible to measurement, more likely to yield a clear determination of the orbital alignment. Everything about TOI-5205b as an observational target flows from that one central fact. The star is small, the planet is large, and the transit is consequently deep. The signal-to-noise is excellent. The transmission spectroscopy signal is large. The Rossiter-McLaughlin effect is accessible. The light curve is clean and unmistakable. The mass ratio of roughly 0.3%, the fraction of the star's mass represented by the planet, is among the highest ever measured in a planetary system, a ratio so extreme that it sits at the very edge of what we previously considered possible for a star-planet pair. All of these exceptional observational characteristics flow downstream from the same source, a gas giant where one should not be, orbiting a star barely large enough to contain it, producing a shadow that announces its existence with a clarity and depth that stands apart from almost everything else in the catalog. The universe, it seems, when it chooses to break the rules, chooses to do so in a way that is clearly visible. The forbidden planet does not hide. Its shadow falls across its star with a boldness that the most sophisticated instruments in space and on the ground can read without ambiguity, can measure with confidence, can use to peel back the layers of a world that had no business existing in the first place. 7%, a simple number, a fraction of starlight blocked by a planet crossing a star. And in that fraction, in that deep, clean, U-shaped valley in a brightness record, the whole improbable story of TOI-5205b is written, waiting for whoever has the instruments and the patience to read it. Let the image of it rest with you now. A graph, just a line, rising and falling, telling the story of a world. The quiet science of measurement, finding the extraordinary hidden inside the ordinary. Numbers that are, in their own way, as beautiful as anything the night sky has to offer. You don't need to hold any of it tightly. Just let it be there, somewhere at the edge of your awareness, as everything around you grows still. A shadow passing across a star. A number recorded. A world found. Segment 8. Environmental conditions, theoretical. There is a particular quality to imagination when it is guided by science. It is different from pure fantasy, from the unconstrained invention of worlds that follow no rules but their own internal logic. It is also different from simple description, from the recitation of measurements and numbers without any attempt to inhabit them. Scientific imagination occupies a middle space between these two modes. It is bounded by what the physics actually permits, shaped by what the measurements actually say, but it reaches toward something more than data. It tries to answer the question that data alone cannot answer. What would it be like? Not what would it be like to survive there. Survival is not on the table for a world like TOI-5205b. But what would it be like to witness it, somehow, impossibly from close range? What would you see, hear, feel, if the laws of physics permitted your presence in a place where they would otherwise be lethal? What is the texture of this world, its quality, its atmosphere in the non-scientific sense of the word, the sense that means mood, character, the feeling a place gives you? Tonight, we're going to let science guide our imagination toward the environmental conditions of the forbidden planet. Not what we know with certainty, because certainty about a world this far away requires observations we're only beginning to make, but what the physics predicts, what the models suggest, what the best current understanding of hot Jupiter atmospheres allows us to reasonably infer. These are theoretical conditions. They are extrapolations from known physics applied to measured parameters. But they are not guesses. They are informed projections. The best picture that careful science can currently paint of what this world is actually like. And the picture, when you look at it as a whole, is one of the most extreme and alien environments that the physics of planetary science can produce. We begin with the wind. In an earlier segment, we explored the concept of tidal locking, the way TOI-5205b has been gravitationally synchronized with its star, so that one hemisphere faces the star forever and the other faces permanently away. This creates a temperature difference between the two sides of the planet that is not subtle. The day side, bathed continuously in stellar radiation, is dramatically hotter than the night side, which receives no direct stellar energy at all. For a planet sitting as close to its star as TOI-5205b does, 2.5 million miles, 1/10 the distance between Mercury and our Sun, this temperature differential is enormous. And enormous temperature differentials drive wind. This is not a complicated physical principle. It is the same mechanism that drives weather on Earth, where the temperature difference between the equator and the poles creates pressure gradients that push air masses from one region to another. Heat a gas and it expands, becoming less dense, creating a region of lower pressure. Cool a gas and it contracts, becoming denser, creating a region of higher pressure. Gas flows from high pressure to low pressure, from the cool side to the hot side, or from the hot side as it rises and the cool side as it sinks, in complex circulation patterns that the atmosphere develops as it tries to equalize the imbalance. On Earth, these circulation patterns produce the winds and weather systems that we experience. On TOI-5205b, the same physical principle operates, but the temperature differential driving it is vastly larger than anything in our own solar system, and the consequences are proportionally extreme. The atmospheric models developed for hot Jupiters, gas giants in close orbits around their stars, consistently predict wind speeds that exceed the speed of sound. Supersonic winds. On Earth, the speed of sound in air is roughly 767 miles per hour at sea level, a speed so fast that aircraft capable of exceeding it must be specially designed to survive the aerodynamic stresses involved. In the atmosphere of a hot Jupiter, The circulation winds are predicted to reach and exceed this speed not at some exotic extreme, but as a general feature of the atmospheric dynamics. The winds at the upper levels of TOI-5205b's atmosphere may routinely reach thousands of miles per hour, carrying heat from the day side toward the night side in vast, planet-girdling jet streams. These are not winds in any sense that relates to human experience. They are not storms or gales, or even the most violent hurricanes on Earth. They are something categorically different. A continuous, permanent, supersonic flow of gas driven by a temperature gradient that never equilibrates, because the gradient is maintained forever by the planet's locked orientation toward its star. There is no season that changes the heating pattern. There is no day-night cycle that periodically redistributes the energy. The day side is always hot, the night side is always cold, and the winds that arise from this eternal imbalance are eternal themselves, permanent features of the planet's atmospheric circulation, as fixed as the hemispheres that drive them. On other hot Jupiters observed by the James Webb Space Telescope and earlier instruments, this circulation has been detected directly. By watching how the brightness of the planet changes as it orbits, measuring the heat it emits from different sides at different orbital phases, astronomers have found that the hottest point on many tidally locked gas giants is not directly beneath the star, as you might expect, but is offset slightly to the east, in the direction of the atmospheric flow. The winds are so powerful that they carry heat faster than radiation can redistribute it, sweeping the thermal maximum eastward from the substellar point. This is the observational fingerprint of supersonic atmospheric circulation, and it is one of the most dramatic demonstrations of large-scale atmospheric dynamics anywhere in the known universe. For TOI-5205b, this same pattern is expected: the perpetual supersonic wind, the offset thermal maximum, the vast, relentless movement of atmospheric gas from one hemisphere to the other and back again, in a circulation that has operated without interruption for billions of years. Now, in those winds, suspended in them, formed from them, drifting through them, are clouds. But not clouds like anything in our sky. At 735 Kelvin, 862 degrees Fahrenheit, hot enough to melt lead and zinc, water does not condense into clouds. Water vapor can exist at these temperatures, but it cannot form droplets. The familiar white clouds that drift across our sky, the thunderheads that build in summer afternoons, the thin cirrus that forms at the edge of the stratosphere, all of these are made of water in one form or another, and none of them could exist in an atmosphere this hot. Water at 735 Kelvin is simply vapor, drifting and unreactive. What condenses at these temperatures? What forms the cloud layers in the atmosphere of TOI-5205b is something else entirely. The models of hot Jupiter atmospheres predict that at temperatures in the range of TOI-5205b, the cloud-forming materials are not water, but minerals and metals. Silicates, the same family of compounds that make up most of Earth's crust, the silicon-oxygen minerals that form quartz and feldspar and olivine, can vaporize at high enough temperatures and then condense into tiny solid particles when the temperature drops sufficiently, much the way water vapor condenses into water droplets when warm air rises and cools. At the right temperature levels in TOI-5205b's atmosphere, silicate particles could condense and form clouds made not of water ice, but of tiny grains of rock. Similarly, certain salts, compounds containing metal atoms bound to simpler anions, have the right thermodynamic properties to condense in this temperature range. Sodium sulfide, potassium chloride, and similar compounds are predicted to form cloud layers in gas giant atmospheres at temperatures around and below 700 to 800 Kelvin. For TOI-5205b, sitting right at the boundary of this temperature regime, these salt clouds are a real possibility. Wispy, high-altitude layers of tiny crystalline particles, drifting in the supersonic winds, forming and dissipating as atmospheric parcels rise and fall through the temperature gradient. And at somewhat higher temperatures and pressures, even metal vapors, iron, magnesium, and other elements that we think of as solid and permanent under any conditions we encounter on Earth, can participate in the cloud formation chemistry of a hot Jupiter atmosphere. On the day side of the most extremely heated hot Jupiters, Iron is actually vaporized into the gas phase and carried aloft, then condenses on the cooler night side into iron rain, liquid droplets of molten iron falling from clouds into the deeper atmosphere below. For TOI-5205b, which is cooler than the ultra-hot Jupiters, where this process is most dramatic. The iron rain scenario is less certain, but the general principle, clouds made of materials that are solid metals and minerals under any conditions familiar to us, applies. Imagine for a moment what this means visually. Clouds made of silicate grains, clouds made essentially of tiny fragments of rock, suspended in an atmosphere of hydrogen and helium, swept along by supersonic winds. Clouds made of salt crystals, clouds that, in some regions and at some altitudes, might be made of material that would be iron or zinc or lead if you could somehow hold it at Earth's temperatures. These clouds would not be white and puffy. They would have colors, ochres and grays, and perhaps dark, smoky tones, depending on their composition and the way they scatter the reddish, infrared-heavy light of the host star. And then there is the question of the magnetic field. For a planet as massive as TOI-5205b, with what is almost certainly an interior that reaches the pressures and temperatures at which hydrogen transitions into a metallic, electrically conducting state, a powerful magnetic field is the magnetic fields of planets are generated by the motion of electrically conducting material in their interiors. On Earth, our magnetic field is generated by the churning of molten iron in the outer core, convective flows of conductive metal driven by the heat leaking from Earth's deep interior. On Jupiter, the conducting material is not iron, but hydrogen. At the extreme pressures present deep inside Jupiter's interior, hydrogen behaves not as a gas or a liquid in any familiar sense, but as a metallic conductor, its electrons freed from their atoms and mobile, capable of carrying electrical current. The convection of this metallic hydrogen, combined with Jupiter's rapid rotation, generates one of the most powerful planetary magnetic fields in the solar system. A field so strong that it creates a magnetosphere extending millions of kilometers into space, trapping energetic particles and creating intense radiation belts. TOI-5205b, with a mass slightly exceeding Jupiter's, almost certainly has a similar metallic hydrogen interior. The pressures deep inside this planet should be sufficient to drive hydrogen into the metallic state. The convection of that metallic hydrogen, driven by the internal heat from tidal forces and residual formation energy, should generate a powerful magnetic field. The exact strength of this field is uncertain, but by analogy with Jupiter, it is likely to be among the most powerful of any planet in the galaxy. This magnetic field plays an important role in the interaction between the planet and its star. The star TOI-5205, as we explored in an earlier segment, regularly produces powerful magnetic flares, violent eruptions of energy that send streams of charged particles and high-energy radiation outward into the surrounding space. For a planet orbiting as close as TOI-5205b does, well within the orbit of any planet in our own solar system, these flares arrive with considerable intensity. The stellar wind, the continuous flow of charged particles from a star's surface, is also far more intense at this close range than it would be farther out. The planet's magnetic field is its primary defense against this particle bombardment. Like Earth's magnetosphere, which deflects the solar wind and channels it around the planet rather than allowing it to directly impact the upper atmosphere. TOI-5205b's powerful magnetic field creates a protective bubble, a magnetosphere, that shields the bulk of the atmosphere from the direct, erosive impact of the stellar wind and flare particles. But the shielding is not perfect. At the outermost edges of the magnetosphere, where the stellar wind pressure exceeds the magnetic pressure, gas can be swept away. Atmospheric escape, the slow, continuous loss of the uppermost atmospheric layers to the stellar wind, almost certainly occurs around TOI-5205b, despite the planet's powerful magnetic protection. High-energy ultraviolet and X-ray radiation from the star, including the bursts produced by flares, heats the uppermost atmosphere, giving the lightest gas molecules enough energy to escape entirely into space in a process called photoevaporation. Over billions of years, this atmospheric escape has stripped away some fraction of the planet's outermost atmospheric material. The rate of this loss, how much gas the planet has lost, and how much it will continue to lose over its remaining lifetime, is one of the open questions that current observational programs are attempting to constrain. Some hot Jupiters observed with ultraviolet telescopes have been found to have extended halos of escaping hydrogen gas, visible as absorption features during transit. TOI-5205b may have a similar halo, a ghostly extension of its atmosphere, being slowly pulled away into space. But it is important to note that this atmospheric escape, while real, is not a catastrophic or rapid process for a planet as massive as TOI-5205b. The planet's strong gravity, 2.5 times Earth's at the cloud tops, provides a powerful counterweight to the escape processes. The deeper layers of the atmosphere are held firmly in place, insulated from the stellar radiation by the overlying layers of gas. The planet is not evaporating on any human-relevant timescale. It is not dissolving or shrinking appreciably over centuries or millennia. The atmospheric escape is a geological timescale phenomenon, meaningful over billions of years, essentially imperceptible over any shorter period. This interplay between escape and retention, between the star's erosive influence and the planet's gravitational resilience, has shaped the atmosphere of TOI-5205b over its entire history and will continue to shape it for billions of years to come. The planet is neither static nor rapidly changing. It is evolving slowly, at the pace that only astronomical timescales permit. The chemistry of that atmosphere, whatever remains after billions of years of this evolution, is expected to include some specific molecules that astronomers are particularly interested in detecting. At temperatures around 735 Kelvin, thermochemical models predict that the dominant carbon-bearing molecule in a hydrogen-rich atmosphere would be carbon monoxide rather than methane. At lower temperatures, methane is the favored form of carbon. At higher temperatures, carbon monoxide takes over. TOI-5205b sits near the transition point, but its temperature suggests carbon monoxide should be relatively abundant in its upper atmosphere. Water vapor is also expected to be present, not as clouds, which cannot form at these temperatures, but as vapor. The signature of water vapor in a hot Jupiter atmosphere has been detected in numerous systems by the James Webb Space Telescope and its predecessors, and it is one of the most sought-after chemical fingerprints in transmission spectroscopy observations. Whether water vapor is detectable in TOI-5205b's atmosphere, and in what abundance, is one of the scientific questions that current and future observations are beginning to address. Now consider the question of moons. In our own solar system, the gas giants are accompanied by extensive moon systems. Jupiter has 4 large moons discovered by Galileo and dozens of smaller ones. Saturn has Titan with its thick nitrogen atmosphere, and a collection of icy companions. Uranus and Neptune have their own families of moons. These moon systems are natural products of the formation process, material left over in the disk around the forming giant planet that coalesces into satellites in much the same way that planets coalesce around a star. But TOI-5205b almost certainly has no moons of any significant size. The reason is gravitational geometry. The planet orbits its star at only 2.5 million miles, an extraordinarily close distance. Any moon that the planet might have formed or captured would find itself in a 3-way gravitational competition between the planet it orbits and the overwhelming nearby presence of the star. The region of space within which a planet can stably hold onto moons, called the planet's Hill sphere, shrinks dramatically when the planet is very close to its star. At TOI-5205b's orbital distance, the Hill sphere is extremely small, and the region of stable satellite orbits within it even smaller. Any moon that tried to form or persist there would be subject to tidal perturbations from the star that would either gradually perturb its orbit outward until the star captured it entirely, or inward until it impacted the planet. The gravitational tug-of-war between planet and star at this proximity leaves no room for stable moons. Similarly, the magnificent ring systems we associate with Saturn, and to a lesser extent, the other giant planets in our solar system, could not persist around TOI-5205b. Ring systems are made of particles, ice, rock, dust, orbiting within a certain distance of the planet. Like moons, ring particles at TOI-5205b's orbital distance from its star would be subject to destabilizing perturbations from the star's gravity. The region of stable particle orbits is too small, the stellar tidal influence too strong. Any ring material that might have existed around TOI-5205b in the past has long since been swept away, and so the forbidden planet is a solitary thing in its immediate environment. No moons, no rings, just the planet itself and the star and the supersonic winds circling from one hemisphere to the other, and the exotic mineral clouds drifting in those winds, and the magnetic field wrapping around everything like an invisible shield against the star's periodic violence. What would it look like if you could somehow be there? Imagine standing, impossibly, theoretically, at the boundary between the day side and the night side of TOI-5205b, at the terminator, the permanent line where eternal day meets eternal night, with the star sitting perpetually on the horizon behind you, never rising higher, never setting. In the direction of day, the sky would glow, but not brightly, not in the way that our daytime sky glows blue and brilliant with scattered sunlight. The star emits mostly infrared radiation, and the atmosphere of the planet scatters and absorbs light differently than Earth's atmosphere does. The visual sky on the day side might be a deep, dusky red-orange, dim enough that a human eye accustomed to Earth's daylight would find it almost twilight-like, despite the ferocious temperatures. The star itself would appear on the horizon as a large, deep red disk, startlingly large given how close the planet sits to it, but not the blazing white-yellow sun of our own experience. A red ember, a vast, dim, ruddy circle. The clouds above, mineral clouds, silica clouds, salt clouds, would drift in the supersonic wind, their colors muted in the reddish light. The horizon in the direction of night would be darker still, fading from the dim orange of the terminator sky into the absolute black of the permanent night side, where no stellar light has ever reached, and where the temperature drops to extremes that our instruments can measure, but our bodies would never survive. And through all of it, through the dim red light and the exotic clouds and the absolute boundary between eternal day and eternal night, the wind would howl. Not a sound you could hear, because there is no medium through which sound could carry to any human listener in this impossible scenario. But the movement would be visible, felt, overwhelming, a continuous planetary scale flow of superheated atmospheric gas, driven by a temperature gradient that will never resolve, that will persist for as long as the planet and star exist together in their improbable, intimate orbit. It is a world of permanent extremes, not changing extremes, not the kind of extremity that cycles and alternates and gives way periodically to something different. Permanent, fixed. The day side always blazing, the night side always dark, the wind always blowing, the exotic clouds always drifting, the magnetic field always deflecting the star's radiation, the atmosphere always slowly, imperceptibly losing its outermost layers to the void. This is the environment of the forbidden planet as our best current understanding can describe it. Not a world that invites, not a world that accommodates, but a world that exists fully, completely, in all its alien extremity, on the other side of 283 light years of dark, patient space. You can let it drift away from you now. The supersonic winds and the mineral clouds and the red twilight of the terminator, the magnetic field and the escaping atmosphere, and the lonely, moonless, ringless giant in its impossible close orbit. Let it all recede to the appropriate distance, a distant thought, at the edge of awareness, growing quieter as everything around you grows quieter too. There is nothing urgent here, nothing that asks anything of you. Only the soft knowledge that somewhere in the constellation of the little fox, a world of extraordinary strangeness is doing exactly what it has always done, circling quietly in the eternal dark between the stars. Segment 9. Comparisons to the solar system. There is a particular way that understanding arrives, not all at once, not in a single flash of comprehension, but gradually, through comparison, through the patient work of holding something unfamiliar next to something known, and letting the relationship between the two slowly illuminate what the unfamiliar thing actually is. This is how we make sense of scale. This is how we metabolize numbers that would otherwise remain abstract. Digits on a page, measurements without meaning, quantities that the mind can repeat without truly grasping. We reach for analogy. We reach for the known. We say, it is like this, but larger. It is like that, but closer. It is the same as what you already understand, except in this one way that changes everything. Tonight, we're going to do exactly that. We're going to bring TOI-5205B home, not literally, not physically, but conceptually. We are going to place it alongside the things we know best, the planets and distances and weights and times that make up our own solar neighborhood, and let those comparisons do the slow, patient work of making the forbidden planet real in a way that raw numbers alone cannot quite achieve. Some of these comparisons will be comforting. They will reveal a familiar shape inside the alien, a recognizable quantity hiding inside the extraordinary. Others will be vertiginous. They will use the familiar as a springboard into a scale that the mind can approach but not fully contain. All of them are invitations. You do not need to hold them tightly. Just let each one open for a moment, breathe, and then drift gently forward to the next. We begin with the most grounding comparison of all. In terms of mass and size, TOI-5205b is the closest thing to a direct twin of Jupiter that the known exoplanet catalog contains. Not an approximate twin, not a rough analog or a distant cousin in the family of gas giants. A near-identical match, 1.08 times Jupiter's mass, 1.03 times Jupiter's radius, with a density hovering in the same range as the largest planet in our solar system. This is a remarkable thing to sit with, because Jupiter is not an abstraction. Jupiter is a world we have visited, not with human beings, not yet, but with machines. The Voyager probes flew past Jupiter in 1979 and sent back the first close-up images of its bands and storms and its 4 large moons. The Galileo probe spent 8 years in orbit around Jupiter, dropping an atmospheric probe into its clouds. The Juno spacecraft has been orbiting Jupiter since 2016, sending back images and data of extraordinary quality and detail. Jupiter is, in some sense, known to us. Not as intimately as Earth, not with the full richness of a world that human eyes have directly observed, but known, measured, characterized, modeled, imaged in detail that fills scientific papers and textbooks. And TOI-5205b is, by the basic physical measurements, the same size, the same mass, the same density. A Jupiter essentially, but placed somewhere else, around a different star, in a completely different set of orbital circumstances, separated from us by 283 light-years of empty space. When astronomers think about what TOI-5205b might look like at the level of its basic structure, they can draw on everything they know about Jupiter and carry it forward. The metallic hydrogen interior, the layered cloud structure in the upper atmosphere, the enormous magnetic field, the deep, crushing pressures at the center. Everything we have learned from decades of observing the giant of our own solar system applies, at least as a starting point, to its twin in the constellation of the little fox. There is something almost tender about this, the idea that the universe would produce, at such extraordinary distance and in such completely different circumstances, something so physically similar to an object we have studied for centuries. Jupiter and TOI-5205b, separated by an almost incomprehensible gulf of space, related by the simple shared fact of what they are made of and how much of it there is. Now let us bring a different comparison to bear, one that is less comforting and more strange. A comparison that asks you to imagine our own solar system transformed. What if you replaced our sun with TOI-5205? Set aside, for a moment, all the questions of orbital mechanics that such a replacement would involve. Simply ask the visual experiential question. What would high noon on Earth look like if our sun were replaced by the small, dim, cool red star that TOI-5205 is? The answer is striking. If TOI-5205 occupied the same position as our sun, at a distance of 1 astronomical unit from Earth, its luminosity is so much lower, its output of visible light so dramatically reduced compared to our own star, that the sky at midday would be darker than what we currently experience on an overcast, cloudy twilight afternoon. Not a slight dimming, not the comfortable diffuse light of a cloudy day, which is still bright enough to read by, still bright enough to fill a room. Something dimmer still, a murky, reddish half-light, the kind of illumination that makes colors hard to distinguish and makes the world feel perpetually on the edge of dusk. The star would be visible, a large, deep red disk in the sky, noticeably bigger in apparent size than our familiar sun because, although it is physically smaller, it emits so little light that you would not be blinded looking toward it. But the landscape around you would be dim. Shadows, where they existed at all, would be soft and indistinct. The sky would likely take on a reddish or brownish cast rather than the brilliant blue we know, because the scattered light would be shifted toward the red and infrared. Plant life, as we know it, which evolved to capture the particular wavelengths of light that our sun produces, would struggle. This thought experiment is not just imaginatively striking, it is scientifically illuminating. It tells us something precise about the nature of TOI-5205's light. Our sun, for all its apparent normalcy to us, is actually a relatively bright and energetic star in the galactic context. We are fortunate, in the narrow biological sense, to orbit a star generous enough with its visible light output to sustain the photosynthetic chains that underpin all complex life on Earth. TOI-5205 offers a fraction of that generosity. It is a dim provider, a miser of photons, a star that burns so slowly and so coolly that the light it produces would leave a human observer at Earth's distance, squinting in something barely brighter than twilight. For the planet actually orbiting TOI-5205, for TOI-5205b pressed close to its star at 2.5 million miles, the situation is different in terms of raw energy received, because proximity compensates somewhat for the star's dimness. But the quality of that energy, its spectral character, its emphasis on infrared rather than visible wavelengths, remains the same regardless of distance. The planet receives a great deal of energy from its star, but most of that energy is infrared. The visual illumination, even on the day side of TOI-5205b, would be dim and reddish in ways that human vision would experience as strangely twilight even in the midst of the equivalent of high noon. Now let us turn from the star to the planet itself, and from the poetic to the almost comically scalar. Because the size of TOI-5205b, when compared directly to Earth, the only planet we have direct bodily experience of, produces numbers that are difficult to absorb without some kind of physical anchoring. The mass first. TOI-5205b is approximately 318 times more massive than Earth. This is the same ratio as Jupiter to Earth, another reminder of the physical twinness of these two worlds. 318 Earths, compressed together under their own gravity, would have the same total mass as TOI-5205b. If you could somehow collect every rock, every ocean, every atmosphere, every core of iron, every human being and building and grain of sand on 318 copies of our planet and press them together into a single object, you would have roughly what TOI-5205b contains. The volume is equally staggering. More than 1,300 Earths could fit inside the volume of TOI-5205b. The planet is not 1,300 times as massive as Earth. Because it is much less dense, its gas giant composition means that the same volume contains much less mass than an equivalent volume of rock and iron. But the sheer interior space of this world, The total volume enclosed within its outer atmosphere could contain more than 1,300 copies of our entire planet, stacked inside it the way you might pack spheres into a larger sphere, until the space was filled. The width is perhaps the most immediately imaginable of these size comparisons. TOI-5205b is approximately 11 times wider than Earth. If Earth were the size of a small, round grape about an inch in diameter, TOI-5205b would be roughly the size of a basketball, not a beach ball, not something absurdly, incomprehensibly larger. A basketball. You could hold the grape in one hand and the basketball in the other, and have, in that physical relationship between your two hands, a reasonably accurate representation of the size ratio between our planet and the forbidden planet. This is one of the places where comparison does its most useful work, where the abstract becomes suddenly, briefly, physically real. 11 times wider. A grape and a basketball. The two objects in your two hands, the same kind of physical scale. The size of a world 283 light years away. Suddenly, something you can feel the proportion of. Now consider what that scale means for weight, for the felt experience of gravity. A person weighing 150 pounds on Earth standing on a scale in a kitchen or a doctor's office, a weight that is utterly ordinary and unremarkable, would weigh more than 350 pounds if they could somehow stand at the cloud top level of TOI-5205b's atmosphere, in the region where the atmospheric pressure matches a standard reference point. The gravity at that level is approximately 2.5 times Earth's surface gravity. Everything is heavier by that factor. Your arms are heavier. Your head is heavier. The effort of simply holding yourself upright against the pull of the planet, an effort so automatic and effortless on Earth that you perform it continuously without any conscious attention, would demand more than twice the muscular work. This comparison, 150 pounds becoming 350 pounds, is not an abstraction. It is something you can physically imagine, at least approximately. Think of carrying another person on your back continuously, while also trying to move normally. Think of the heaviness in your legs after a long, exhausting day multiplied and made permanent and inescapable. The gravity of TOI-5205b would be felt in every cell of a human body, a continuous, pervasive, inescapable heaviness pressing inward from every direction. It would be, in a physical sense, crushing, not instantly lethal at 2.5 times Earth's gravity, but profoundly debilitating. Something that no human biology is equipped to sustain. And yet to the planet itself, this gravity is simply what it is. It is the natural, unremarkable condition of an object with that much mass. TOI-5205b does not experience its own gravity. It simply is. Let us turn now to the comparison of time, which is perhaps the most disorienting of all the ways in which the forbidden planet differs from our familiar solar neighborhood. A year on TOI-5205b, one complete orbit around its star, lasts 1.63 Earth days, shorter than a standard weekend. From Friday evening to Sunday evening, as experienced by a human being going about an ordinary week, is roughly 48 hours, 2 full Earth days. TOI-5205b completes more than one full year in that same span of time. By the time Sunday evening arrives, the forbidden planet has already lived through more than one complete orbit, more than one complete year, more than one full cycle of whatever seasons or astronomical events its orbital period defines. The mind can repeat this fact without fully inhabiting it. But try for a moment to really sit with it. Think of everything a year contains in human experience. The full turn of seasons, the accumulation of days and weeks and months, birthdays and anniversaries, and the slow passage of time that marks how we age and change and move through our lives. A year is a meaningful unit. It has weight and duration. On TOI-5205b, that entire cycle, one complete orbit, one complete year, takes 39 hours, less than 2 of your days. The planet has lived through more years in the time you have been asleep tonight than you will live through in the rest of your life. And speaking of Mercury, the closest planet to our own sun, the world we consider the most extreme in its proximity to its star, let us place TOI-5205b alongside it. because this comparison perhaps most viscerally captures the orbital situation of the forbidden planet. Mercury orbits the Sun at an average distance of about 36 million miles. TOI-5205b orbits its star at about 2.5 million miles. This means that TOI-5205b is 14 times closer to its star than Mercury is to ours. 14 times. If you took Mercury's already extreme orbital proximity and divided it by 14, you would have the orbital distance of the forbidden planet. Mercury, already a world of such extreme stellar proximity that its surface reaches temperatures high enough to melt lead, is 14 times farther from its star than TOI-5205b is from TOI-5205. And what would the star look like from that distance? If you were floating impossibly in the upper atmosphere of TOI-5205b, drifting in the supersonic winds, suspended in the layer of mineral clouds, and you look toward the direction of the star, what would you see? You would see a star that fills the sky in a way that has no parallel in our solar system. Because TOI-5205 is physically small, barely larger than Jupiter, remember, its apparent size of the sky, at 2.5 million miles distance, would be enormous. Not the small, brilliant disk that our sun presents in our sky, an object you can cover with your thumb held at arm's length, a disk that, despite its overwhelming brightness, occupies only about half a degree of arc in our sky. No, from TOI-5205b's vantage point, the star would appear as an immense, imposing presence, a large reddish disk dominating the sky in the direction of perpetual day, filling a substantial portion of the visual field. Not a point of light, not even a disk you could comfortably look at without it commanding your entire attention. A wall of dim red light, vast in its apparent size, permanent and unmoving, never setting, never shrinking, always there. It would be a sky unlike any human eye has ever seen, a sky defined by the presence of something enormous and close and permanent, in a way that our experience of the sun, distant enough that it appears small, bright enough that you cannot look at it, simply does not prepare us for. And finally, the longest view, the comparison of timescales so vast that they dwarf everything else we have considered tonight and push into the territory our own Jupiter, the physical twin of TOI-5205b, the planet whose measurements so nearly match those of the forbidden planet, has a fate. It is not the fate of geological transformation or slow atmospheric evolution, but the fate of destruction. In approximately 5 billion years, our sun will exhaust the hydrogen fuel in its core and begin the transformation that turns it into a red giant star, expanding enormously, engulfing the inner planets, possibly reaching as far as Jupiter's current orbit. As the sun expands and its outer layers drift away into space, the planets of our solar system will be disrupted, scattered, or consumed. Jupiter's ultimate fate in this transformation is uncertain, but it faces a solar system that will, in 5 billion years, be fundamentally and permanently changed. The sun, as it is, will not last forever, and Jupiter exists within a system whose central star is mortal. TOI-5205b exists in a different relationship with time. Its host star, TOI-5205, is a red dwarf, burning its fuel so slowly, so conservatively, that it will remain on the main sequence for hundreds of billions of years, possibly approaching 1 trillion years. The star will still be burning, still fusing hydrogen in its core, still radiating its dim infrared light into space, still tugging TOI-5205b around in its 1.63-day orbit, long after our sun has died, long after our solar system has been transformed beyond recognition, long after Earth itself has ceased to exist in any form recognizable to us. While Jupiter's solar system is counting down in the vastly slow way that stellar evolution counts, in billions of years rather than thousands, TOI-5205b is not. It sits in the shelter of a star so long-lived that the word forever becomes almost inadequate. Our entire solar system, from formation to the sun's death, spans roughly 10 billion years. TOI-5205b will still be orbiting its star in that same 1.63-day circle, when 10 billion years from now is already ancient history. When 100 billion years from now is already ancient history. The forbidden planet will outlive our solar system by a margin that makes our solar system seem brief. There's something in this that asks for a particular quality of attention, not the urgent attention of something happening now, but the slow, geological, astronomical attention of something that simply endures. The forbidden planet will be there after everything we know is gone, after the sun that warms our days has spent itself and faded to a cooling remnant, after the planets we know by name have scattered or been consumed, after every trace of human civilization has been transformed beyond recognition by time. TOI-5205b will still be there, circling, permanent, indifferent, surviving. Let these comparisons settle now, one by one, as gently as leaves settling to the floor of a still room. The grape and the basketball, the 150 pounds becoming 350, the weekend containing a year, the star filling the sky, the endurance that outlasts everything we know. None of it asks anything of you. None of it requires a response or a resolution. It is simply the universe doing what it does, existing at scales that exceed our grasp, presenting us with proportions that the mind can approach but not fully hold, offering, in each new comparison, another glimpse of how large and strange and patient it all is. You are very small and very briefly here, and that is perfectly fine. The universe has room for small and brief things. It has room for brief things that notice it, even from this distance, even for just this little while. Let everything go quiet now. Let the comparisons drift away. Let the basketball and the grape and the red sky and the 39-hour year all dissolve back into the dark from which they briefly emerged. Segment 10, Scientific Significance and the Future. We have come a long way together. Over the course of these segments, we have traveled slowly, quietly, without hurry, from the most basic facts about a planet's name and catalog designation, through the star that hosts it and the orbit it follows and the physical conditions it endures, through the story of how it was found and what its measurements reveal, through comparisons that tried to bring its alien scale into contact with things we know and can feel. And now we arrive at the last stop on this particular journey. Not the end of the story, because the story of TOI-5205b is far from finished, and in many ways has barely begun. But the end of tonight's telling of it, the place where we step back from the details and ask the largest question: why does any of this matter? What does the forbidden planet mean, not just as a curiosity or an anomaly, but as a scientific object, as a challenge to human understanding, as a window into questions that science has not yet answered? These are the questions worth sitting with as you drift toward sleep. Not technical questions requiring effort or concentration. Just the broad, gentle, open questions that the universe has always been best at posing. Questions whose very existence is more valuable than any answer we currently possess. Let us begin at the frontier of what is currently happening in the scientific study of this world. Among the most powerful scientific instruments that humanity has ever constructed is the James Webb Space Telescope. Launched in December of 2021, fully operational since the summer of 2022, positioned nearly 1 million miles from Earth at a gravitationally stable point called the second Lagrange point, where it orbits the Sun in company with Earth, but forever faces away from the Sun's glare. The James Webb Space Telescope was built to see the early universe, to detect the infrared light of the first galaxies that formed in the hundreds of millions of years after the Big Bang, redshifted by the expansion of space into wavelengths that no previous telescope could reach with sufficient sensitivity. It represents decades of engineering effort, billions of dollars of investment from multiple space agencies across multiple countries, and some of the most precise optical fabrication ever achieved. It was also built to study exoplanet atmospheres, and TOI-5205b has been designated in the prioritization language that astronomers use for allocating precious telescope time as a Tier 1 target. Tier 1 means the highest priority. It means the planet is considered among the most scientifically valuable targets that the James Webb Space Telescope can study. That the expected scientific return from observations of this world is exceptional enough to justify allocating the irreplaceable resource of telescope time to it ahead of a great many other compelling candidates. In a catalog of thousands of known exoplanets, being designated Tier 1 for James Webb is a distinction that reflects genuine scientific consensus about where the most important work can be done. Why is TOI-5205b Tier 1? The reasons flow directly from everything we have explored in these segments. The transit depth is enormous, 7%, providing a transmission spectroscopy signal that is dramatically stronger than what most exoplanets produce. The host star, while dim, is small enough that the planet's atmosphere leaves a proportionally large fingerprint in the starlight during transit. The planet occupies a scientifically interesting position in the space of planetary parameters, a gas giant around an M-dwarf, a formation puzzle, an object whose atmospheric chemistry may encode the history of its birth. And the James Webb Space Telescope is an infrared instrument optimized for exactly the wavelengths at which both TOI-5205 and TOI-5205b emit and absorb most strongly. When the James Webb Space Telescope observes TOI-5205b during transit, collecting the starlight that filters through the planet's atmosphere and dispersing it into its component wavelengths with the telescope's spectroscopic instruments, it will see a spectrum, a detailed record of which wavelengths of light were absorbed by the atmosphere and which passed through freely. And in that spectrum, encoded in the precise pattern of absorption features, is the chemical composition of the planet's upper atmosphere. Water vapor has its fingerprints. Carbon dioxide has its fingerprints. Carbon monoxide, methane, ammonia, hydrogen sulfide. Each molecule absorbs specific, characteristic wavelengths of infrared light, and each one that is present in the atmosphere of TOI-5205b will leave its mark in the James Webb spectrum. By reading those marks, by identifying which molecules are present and in what relative abundances, astronomers can begin to characterize the chemistry of a world that sits 283 light-years away. But the James Webb observations are not just about knowing what is in the atmosphere for its own sake. They are instruments of investigation into the deepest remaining mystery of this planet. Where did it come from? How did it get here? What is the story of its formation and migration that brought it to where it orbits today? Two fundamentally different scenarios are possible. In the first scenario, TOI-5205b formed where it is now, or very close to it, in the inner regions of the protoplanetary disk, from whatever material was available in that region. In the second scenario, the planet formed much farther from a star, out in the cold, material-rich outer regions of the disk, where building a massive planetary core is more achievable, and then migrated inward over time, driven by interactions with the disk itself or with other planetary bodies, until it arrived at its current tight orbit. These two scenarios would leave different chemical traces in the planet's atmosphere. The composition of a planet's atmosphere reflects, at least partially, the composition of the material from which it formed, which in turn reflects where in the protoplanetary disk that material originated. The disk is not chemically uniform. Different regions have different temperatures, different condensation fronts, where specific chemical compounds freeze out of the gas phase into solid ice, different relative abundances of carbon and oxygen and other elements. A planet that formed in the cold outer disk would have incorporated different ices and solids than a planet that formed in the warm inner disk. And those different formation environments would leave different chemical signatures, preserved in the atmosphere, readable through spectroscopy. One of the most powerful of these chemical diagnostics is the ratio of carbon to oxygen, the C2O ratio, in the planet's atmosphere. The carbon-to-oxygen ratio is sensitive to where in the disk a planet formed, because the relative abundances of carbon and oxygen in the gas and solid phases change dramatically across the disk's various condensation fronts. A carbon-to-oxygen ratio that is high, more carbon relative to oxygen, suggests formation in certain disk regions. A ratio that is low suggests others. By measuring this ratio in TOI-5205b's atmosphere through James Webb spectroscopy, astronomers hope to triangulate backward, to read the chemical history of the planet's birth and trace it to a specific location in the protoplanetary disk, where the planet spent its early life. This is genuinely remarkable science. The idea that we can measure, from a distance of 283 light-years, a chemical ratio in a planet's atmosphere and use it to determine where in a disk that no longer exists, that dispersed billions of years ago, the planet was born, is an extraordinary demonstration of what careful physics and advanced instrumentation can achieve. The disk is gone. The early solar system of TOI-5205 is ancient history, preserved now only in the architecture of what survives. But the chemistry of the atmosphere carries the memory forward, encoded in ratios and abundances that the universe maintains as patiently as any archive. Alongside the carbon-to-oxygen ratio, astronomers are actively searching for another chemical diagnostic: the overall abundance of heavy elements heavier than hydrogen and helium, in the planet's atmosphere. In our own solar system, Jupiter and Saturn are both enriched in heavy elements compared to the Sun. They contain more carbon, more nitrogen, more sulfur, more of the trace elements that were incorporated when their cores swept up solid material from the protoplanetary disk. The degree of this enrichment carries information about how much solid material the planet incorporated during its formation, and this, in turn, constrains the formation scenario. If TOI-5205 is strongly enriched in heavy elements, it suggests a formation history that involves substantial accretion of solid planetesimals, consistent with a core accretion scenario, possibly in a region of the disk rich enough in solids to build a substantial core. If it is relatively unenriched, if its atmosphere is essentially pristine hydrogen and helium with few heavy element additions, it suggests a different history, perhaps one involving rapid formation by gravitational disk instability rather than core accretion. Every measurement adds a constraint. Every constraint narrows the range of possible histories. And eventually, from the accumulation of enough constraints, a clear picture of how this planet came to be may emerge. There is another dimension to the ongoing investigation of this planet that is worth pausing on, one that reveals how discovery, in modern astronomy, is never really finished with a single paper or a single instrument. Ground-based observatories continue to monitor the TOI-5205 system, watching for subtle variations in the timing of the planet's transits. Transit timing variations. Tiny deviations in exactly when a transit begins, measured against the prediction of a perfectly regular orbital clock, can reveal the presence of other bodies in the system. If an additional planet orbits TOI-5205 somewhere, perhaps a smaller, rocky world, too small to produce a detectable transit of its own, its gravitational influence would subtly perturb the orbit of TOI-5205b, causing the gas giant's transits to arrive slightly early or slightly late in a pattern that encodes the hidden planet's properties. This is a powerful detection method because it allows astronomers to infer the existence of planets that they cannot directly see. By listening for the gravitational whisper those planets leave in the timing of a planet they can see. Whether TOI-5205 harbors smaller siblings for its enormous gas giant is a genuinely open question. We noted in an earlier segment that the formation of TOI-5205 likely consumed most of the available solid material in the disk, making large planetary siblings unlikely. But smaller rocky worlds, built from the last remnants of disk material, cannot be ruled out. The transit timing monitoring, ongoing at ground-based facilities, represents a patient, continuous search for exactly these kinds of gravitational whispers. And then there is a question about the relationship between the planet and its star that moves in the opposite direction, not from the planet's influence on the star's timing, but from the star's influence on itself, possibly mediated by the planet's proximity. Astronomers are studying whether the close orbital presence of TOI-5205 might be triggering or enhancing the stellar flares that TOI-5205 produces. This is not an outlandish suggestion. It is grounded in physical mechanisms. A massive planet in a very close orbit creates tidal stresses on its host star, in addition to the tidal stresses it experiences itself. These stellar tidal stresses can, in principle, influence the star's internal dynamics, potentially affecting how its magnetic field behaves and how often and how powerfully it produces flares. There is also the possibility of direct magnetic interaction. If the planet's own powerful magnetic field is close enough and strong enough to interact with the stellar magnetic field, this coupling could influence flare activity. Evidence for this kind of star-planet magnetic interaction has been tentatively found in a handful of other close-in hot Jupiter systems, where flare rates appear elevated in ways that correlate with the planet's orbital position. Whether this effect is real and significant in the TOI-5205 system is an active area of investigation. The implications, if confirmed, would be significant. They would add another layer of complexity to the environmental conditions of the planet, which would be exposed to an even more active flaring environment than the star's baseline activity already provides. Beyond the investigations of this one system, TOI-5205b has placed itself at the center of a broader statistical effort in the astronomical community. Astronomers are conducting large-scale surveys of M-dwarf planetary systems, looking at hundreds and eventually thousands of red dwarf stars with the sensitivity needed to detect gas giants, in an attempt to determine how common or rare objects like TOI-5205b actually are in the galaxy. Is this planet a one-in-a-million accident, the product of an extraordinarily unlikely chain of circumstances that will almost never repeat? Or is it the tip of an iceberg, the most obvious and easily detected member of a class of planets that form around M-dwarfs more commonly than our models predicted, but that have mostly gone undetected because we were not looking carefully enough? The answer to this statistical question will profoundly shape how we revise our models of planet formation. If TOI-5205b is truly unique or nearly so, then perhaps it represents a rare concatenation of favorable conditions, a slightly metal-rich disk, a particularly efficient pebble accretion event, a fortunate combination of timing that will not often recur. If it is merely the most prominent example of a broader population, then something fundamental about our understanding of how gas giants form must be revised much more substantially. The models must be wrong not just in this one case, but across a significant fraction of M-dwarf systems. The statistical work is not complete. The surveys are ongoing, but every new M-dwarf system studied, every new set of data from ground-based spectrographs and space-based photometers, adds another data point to the picture of what is typical and what is exceptional around the most common type of star in the galaxy. And all of this ongoing scientific activity, the James Webb observations, the transit timing monitoring, the stellar flare investigations, the large-scale surveys, flows downstream from one original fact, from the detection by a satellite in orbit around Earth of a 7% dip in the brightness of a small, faint star in the constellation of the Little Fox. Everything that has followed and everything that will follow traces back to that first signal, that first shadow. TOI-5205b belongs in the taxonomy that astronomers are now beginning to construct to a newly recognized category of objects, ultramassive planets around ultra-low-mass stars. This category did not exist before discoveries like this one created it. The scientific literature did not have a well-populated box for gas giants of Jupiter's mass orbiting M-dwarfs of this type, because such objects were not expected to exist in numbers significant enough to warrant a category. Now they have one. The category may be small. It may contain only a handful of well-characterized members, but its existence represents a conceptual shift. It says that this combination of properties, however improbable our models said it was, is a real and repeating feature of the universe's construction of planetary systems. It is not a one-time error in nature's calculations. It is a category, a type, a thing that the universe does. And because the universe does it, because TOI-5205b exists unambiguously in the catalog of confirmed exoplanets, the textbooks must change. Not metaphorically, not eventually, not as a future aspiration. The chapters on planetary formation in astronomy and planetary science textbooks must be revised to accommodate this reality. The simplified story of core accretion, which worked well enough as an approximation when we only knew about planets in our own solar system, and which held up reasonably well through the early decades of exoplanet discovery, is no longer sufficient. It is incomplete. It predicts things that are not true and fails to predict things that are. The revision of scientific understanding is sometimes portrayed as a crisis, as a failure, an embarrassment, a sign that the previous science was wrong. But this is a misunderstanding of how science actually progresses. The previous models were not wrong in the sense of being carelessly made or poorly reasoned. They were the best available synthesis of the evidence that existed at the time they were constructed. And they remain useful. They explain a great deal. They make accurate predictions in many contexts. They are not simply discarded, but are refined and extended. What the discovery of TOI-5205b does is identify the boundary of their validity. It says the model works here, and here, but not here. And in identifying that boundary precisely, it points toward what must be added, what must be modified, what new physics or new mechanisms must be incorporated to build a more complete picture. This is how knowledge grows, not by accumulating confirmations of what we already believe, but by finding the places where what we believe runs out, where the world is larger and stranger than our current framework can contain. Every great discovery in science is, at some level, a discovery of a boundary, a place where our maps end and the territory continues. TOI-5205b is one of those places, and it is, in this final sense, the most important thing about it. More important than its transit depth, or its mass, or its orbital period, or its exotic mineral clouds, or its supersonic winds. More important than any of the specific, measurable, characterizable facts we have explored across these segments. The most important thing about the Forbidden Planet is the lesson it carries, a lesson that is ancient and recurring in the history of science, and that always arrives fresh, always arrives with the same quiet power. Whenever a new piece of the universe reveals itself to be more than our models predicted. The lesson is this: the universe is more creative than we are. Our equations are good. Our models are careful. Our theories are built by some of the finest minds our species has produced, refined over decades, tested against every observation we could make. And still, the universe builds things we did not expect. Still, it arranges matter and gravity and time in configurations that fall outside the range of what our best thinking said was possible. Still, it surprises us, not because it is trying to, not because it has any interest in our theories or any awareness of our expectations, simply because it is vast and complex and ancient and operates by rules whose full implications we have not yet worked out. Because 13.8 billion years of physical processes, operating across scales from the quantum to the cosmic, produce combinations of circumstances that no finite set of models, built by creatures who have been doing science for a few centuries, can fully anticipate. The Forbidden Planet is a reminder of this, a specific, measurable, peer-reviewed reminder, published in the Astrophysical Journal Letters, orbiting a star in the constellation of the Little Fox, 283 light-years from the world on which the beings who found it are briefly living. The universe is larger than our understanding of it. It always has been. It always will be. And the distance between what we understand and what is true is not a source of frustration or inadequacy. It is the source of all future discovery. It is the gap that science exists to explore. It is the reason there will always be more to find. You are part of a species that found this planet, that built the instruments capable of detecting a 7% dip in the brightness of a star too faint to see without a telescope. that designed and launched and operates the James Webb Space Telescope, floating 1 million miles away in the dark, collecting light from worlds we will never visit, that wrote the papers and ran the simulations and argued about the physics and revised the models, and will continue doing all of these things patiently and carefully, for as long as the planet that produced us continues to support the asking of questions. That is no small thing, to be the kind of creature that asks, that notices a shadow in the light of a distant star and asks what is casting it, that is not satisfied with the answer our models predicted and keeps looking until it finds what is actually there. You carry this curiosity with you, even now, even here, even as everything grows quiet and the weight of the day dissolves and the thoughts grow softer and less distinct. The wondering does not stop. It simply changes quality. It becomes less sharp-edged, less urgent, more like a background warmth than an active fire. The questions remain, but they no longer demand answers tonight. They are content to simply be there, somewhere at the edges of awareness, like distant stars, present, patient, real. The forbidden planet is out there, orbiting its star in 1.63 days, over and over, as it has been doing for billions of years and will continue to do for billions more. The James Webb Space Telescope is out there, floating in the dark 1 million miles from Earth, collecting photons from distances that beggar imagination. The scientists are there in their offices and observatories and classrooms, asking the questions that the universe keeps answering in unexpected ways. And you are here, small and warm and briefly conscious in the midst of an incomprehensibly vast and ancient universe that is still, after all this time, full of things no one has found yet, full of things that break the rules we thought were permanent, full of forbidden planets and impossible orbits and shadows in the light of distant stars. It is enough. It is more than enough. It is, in fact, extraordinary. Let everything go quiet now. Let the questions rest. Let the forbidden planet orbit in peace, 283 light-years away, in its patient and impossible circle around a star barely large enough to hold it. Let sleep come. The universe will still be there in the morning, vast and strange and waiting, full of things that should not exist and do. Rest now.